Imagine standing on a beach at night, the gentle waves lapping at your feet as you gaze upward at the stars. They seem so close, don't they? Tiny pinpricks of light scattered across the dark canvas of our night sky. Some appear to twinkle more brightly than others, giving the impression that they might be just a little bit closer to us, perhaps close enough to reach out and touch. But appearances can be deceiving, especially when we contemplate the cosmos. The nearest star to Earth is, of course, our Sun, a blazing sphere of hydrogen and helium, approximately 150 million kilometers away from us. Light from the Sun takes about 8 minutes to reach our planet. 8 minutes. That doesn't sound too distant, does it? But beyond our Sun lies a vastness that challenges human comprehension. Proxima Centauri, our stellar next-door neighbor, sits approximately 4.2 light-years away from Earth. A light-year, the distance light travels in one Earth year, spans about 9.5 trillion kilometers. To put this in perspective, if you could travel at the speed of our fastest spacecraft, it would take you tens of thousands of years to reach even this closest star beyond our Sun. When we speak of proximity in cosmic terms, we enter a realm where familiar measurements lose their meaning. The stars we consider nearby are so distant that the light we see from them began its journey to Earth years, decades, or even centuries ago. What we observe when we look at the night sky is not what is, but what was. Yet these distant neighbors call to us. They beckon humanity forward with silent promises of discovery, of wonder, of potential homes and resources beyond our own fragile world. They represent the next great threshold for our species, the boundary between being a planetary civilization and becoming a truly stellar one. In the quiet moments between twilight and dawn, when the stars shine their brightest, it's easy to feel a connection to these distant suns. Perhaps it's because we know, on some fundamental level, that the elements in our bodies were forged in stellar furnaces billions of years ago. We are, in a very real sense, children of the stars. The journey to reach our stellar neighbors will be the greatest expedition humanity has ever undertaken. It will test the limits of our technology, our patience, our cooperative spirit, and our imagination. It will require us to think not in terms of years or decades, but in centuries and millennia. It will challenge us to envision futures where the travelers who depart may not be the ones who arrive, where messages sent might not receive replies for generations. Yet throughout human history, we have always been explorers. From the first humans who left Africa to spread across the globe, to the sailors who crossed vast oceans without certainty of what lay beyond, to the astronauts who took our first tentative steps beyond Earth's atmosphere, we have always been driven to see what lies over the next horizon. The stars represent our ultimate horizon. They wait for us, patient and eternal by human standards. They have witnessed the entire span of human civilization, from our first tentative use of fire to our modern technological society, all in the blink of a cosmic eye. And when we look up at those stars, consider for a moment the sheer scale of what we are observing. The light from Proxima Centauri that reaches your eyes tonight began its journey more than 4 years ago. From Sirius, one of the brightest stars in our night sky, that light has been traveling for over 8 years. From Deneb, a star visible in the constellation Cygnus, the light has been journeying for over 1,500 years. When that light began its journey toward Earth, the Roman Empire had fallen, and much of Europe was entering what we now call the Dark Ages. This is the poetry of cosmic distance. Each star we see represents not just a different place, but a different time. We are looking back into history with every upward glance. And yet, despite these vast distances, we dream of reaching these stars. It is perhaps the most audacious dream humanity has ever dared to dream. Compared to interstellar travel, all our previous explorations pale in comparison. Crossing oceans, climbing mountains, even landing on the moon, and sending robots to Mars. All these achievements magnificent as they are, represent merely the first faltering steps of a child learning to walk. Reaching the stars would be our species' first true adult stride. But how do we cross such immense distances? How do we traverse the gulf of light years that separates us from even our closest stellar neighbors? What technologies would we need to develop? What resources would we need to harness? What sacrifices might be required? And perhaps, most importantly, what would we find when we arrived? These are the questions that will guide our journey together. We will explore the current state of our space exploration efforts, the technologies that might one day carry us to the stars, the challenges we must overcome, and the wonders that may await us there. So as we begin this gentle journey of contemplation together, let us approach the stars with both scientific precision and poetic wonder. Let us consider what it would mean to reach out across the void of space and touch these distant suns, not as conquerors, but as explorers, as learners, as dreamers. For the story of humanity's journey to the stars is not just about rockets and physics and technology. It's about who we are as a species, about our place in the cosmos, about the legacy we hope to leave in the universe. It's about transforming ourselves from beings bound to a single world to creatures who can make homes among the stars. So take a deep breath, relax, look up at the night sky with new eyes, and let us begin our journey together, across the immense distances of space, toward the stellar neighbors that have shone down upon us since the dawn of humankind. The path is long, the challenge is immense, but the calling of the stars is ancient and profound. They have guided sailors across oceans, inspired poets and scientists alike, and now they beckon us to the greatest journey we will ever undertake. The stars are waiting, and slowly, steadily, we are preparing to answer their silent call. Our journey to the stars must begin with understanding the scope of our current reach. Like a child learning to crawl before walking, humanity has been gradually extending its grasp beyond the cradle of Earth. We have taken our first tentative steps into the cosmic ocean, and before we can contemplate voyaging to other stars, we must appreciate the vastness of our own solar neighborhood. The Moon, our celestial companion, orbits at an average distance of 384,400 kilometers from Earth. This distance, while vast by terrestrial standards, is close enough that light from the Moon reaches us in just over 1 second. It represents our first stepping stone into space, the first world beyond our own that humans have physically touched. The Apollo missions of the 1960s and early 1970s represented humanity's first true venture beyond our home planet. When Neil Armstrong and Buzz Aldrin stepped onto the lunar surface on July 20th, 1969, they expanded the boundaries of the human experience in a profound way. For the first time, human beings walked on another world, gazed back at the Earth from afar, and returned to tell the tale. The journey to the Moon took Apollo astronauts approximately 3 days. Even at this relatively modest cosmic distance, the challenges were immense. The spacecraft needed to escape Earth's gravity, navigate the void between worlds, land safely on an airless body, and then return home. Each of these steps required innovations in propulsion, life support, navigation, and materials science. Yet the Moon, as significant as it is in our space exploration history, sits practically at our doorstep in cosmic terms. It is so close that amateur astronomers can see its craters with modest telescopes, and professional observatories can study individual boulders on its surface. Radio communications with the Moon experience a delay of only about 2.5 seconds round trip, allowing for almost real-time conversation between Earth and lunar explorers. The true challenge of reaching the Moon was not primarily the distance, but rather the energy required to escape Earth's gravitational pull. The Saturn V rocket, which carried the Apollo astronauts to the Moon, remains the most powerful launch vehicle ever built. Standing over 110 meters tall, it produced more thrust than 85 Hoover dams at liftoff. This immense power was necessary just to escape the gravitational well of our home planet and set a course for our nearest celestial neighbor. After the Apollo era, human exploration beyond Earth orbit paused. but our robotic emissaries continue to push outward. The Lunar Reconnaissance Orbiter, launched in 2009, has been mapping the Moon in unprecedented detail, identifying potential resources and landing sites for future human missions. The Chang'e missions from China, including the first landing on the lunar far side, have expanded our understanding of lunar geology. Private companies and international space agencies are now planning new human missions to the Moon, establishing what may become a permanent human presence on another world. Moving outward from the Moon, our next celestial neighbor is Venus, the second planet from the Sun. At its closest approach to Earth, Venus comes within about 38 million kilometers of our world. At this distance, light takes just over 2 minutes to travel between our planets. Venus represents a significant leap in distance from the Moon, and correspondingly, our explorations of Venus have been limited to robotic probes rather than human visitors. The Soviet Venera program, which launched a series of spacecraft to Venus between 1961 and 1984, represented humanity's first successful attempt to land probes on another planet. Though these landers survived for only short periods in the harsh Venusian environment, with surface temperatures hot enough to melt lead and atmospheric pressure 90 times that of Earth at sea level, they sent back our first direct measurements and images from the surface of another planet. More recent missions, like the European Space Agency's Venus Express and Japan's Akatsuki, have studied Venus from orbit, mapping its dense, cloud-covered atmosphere and searching for clues about why this planet, so similar to Earth in size and composition, evolved into such a hostile world. These missions prepare the way for future, more ambitious exploration of Venus, including potential airborne platforms that could float in the more temperate upper atmosphere, where conditions are surprisingly Earth-like. Beyond Venus, we encounter Mars, a world that has captured human imagination like no other planet. Mars orbits the Sun at an average distance of about 228 million kilometers, but its elliptical orbit brings it as close as 55 million kilometers to Earth during favorable oppositions. At its closest, light from Mars takes about 3 minutes to reach Earth. Mars has been the target of numerous robotic missions, from the early Mariner flybys of the 1960s to the sophisticated rovers of the 21st century. The Curiosity and Perseverance rovers have driven across the Martian landscape, drilling into rocks, analyzing soil samples, and sending back stunning panoramic images of rust-colored plains and mountains. These robotic explorers have found evidence of ancient rivers, lakes, and potentially habitable environments on what is now a cold, dry world. The journey to Mars takes significantly longer than a trip to the Moon. Depending on the relative positions of Earth and Mars in their orbits, spacecraft typically take between 6 and 9 months to travel between the planets. This duration begins to introduce new challenges for human exploration, including prolonged exposure to radiation and microgravity, psychological effects of isolation, and the need for robust, long-duration life support systems. Yet despite these challenges, Mars represents a tantalizing destination for future human exploration. Its day is similar in length to Earth's. Its gravity is about 38% of Earth's, and it has an atmosphere, albeit a thin one, that could provide some protection from radiation and meteoroids. Mars also has abundant resources, including water ice at its poles and just beneath the surface in many regions, which could be extracted and processed to provide water, oxygen, and rocket fuel for human explorers. The journey to Mars represents a crucial stepping stone in our evolution as a spacefaring species. It requires us to develop technologies and capabilities that will serve as the foundation for more ambitious journeys beyond. In situ resource utilization, closed-loop life support systems, radiation shielding, long-duration propulsion, and autonomous operation are all essential capabilities for Mars missions that will be even more critical for eventual interstellar travel. Yet even Mars, with all its remoteness, still sits within the inner solar system, relatively close to our Sun. To truly grasp the scale of our solar system, we must venture beyond the orbit of Mars into the realm of the outer planets. Between Mars and Jupiter lies the asteroid belt, a region populated by millions of rocky and metallic objects ranging in size from dust particles to dwarf planets. The largest object in the asteroid belt, Ceres, has been visited by NASA's Dawn spacecraft, which orbited and studied this small world from 2015 to 2018. Ceres, despite its modest size, about 940 kilometers in diameter, has revealed itself to be a complex world with a layered interior, including a substantial amount of water, ice, and possibly a subsurface ocean. Other spacecraft, like Japan's Hayabusa 2 and NASA's OSIRIS-REx, have visited smaller asteroids and even returned samples to Earth, providing insights into the building blocks of our solar system. These missions demonstrate our growing capability to navigate among the smaller bodies of our solar system and to extract resources that may one day support human exploration and settlement. Jupiter, the largest planet in our solar system, orbits at an average distance of 778 million kilometers from the Sun. At its closest approach to Earth, Jupiter is still about 628 million kilometers away, a distance that light crosses in about 35 minutes. The Galileo spacecraft, which studied Jupiter and its moons from 1995 to 2003, took 6 years to reach the Jovian system, using a complex series of gravity assists from Venus and Earth to build up enough speed for the journey. More recently, the Juno spacecraft, which entered orbit around Jupiter in 2016, has been studying the giant planet's interior structure, magnetic field, and atmosphere, providing unprecedented insights into the formation and evolution of the largest planet in our solar system. Juno's mission has been extended to explore Jupiter's moons, including Europa, which harbors a global ocean beneath its icy crust, and may be one of the most promising places in our solar system to search for extraterrestrial life. Saturn, with its magnificent rings, lies even farther out, at an average distance of 1.4 billion kilometers from the Sun. Light from Saturn takes about 1 hour and 20 minutes to reach Earth. The Cassini mission, one of our most ambitious planetary exploration efforts, took 7 years to reach Saturn after its launch in 1997. Cassini spent 13 years orbiting Saturn, studying the planet, its rings, and its moons in unprecedented detail. It revealed Titan to be a world with lakes and seas of liquid methane and ethane, complete with a methane cycle analogous to Earth's water cycle. It discovered plumes of water ice erupting from the south pole of Enceladus, indicating the presence of a subsurface ocean that may have conditions suitable for life. And it studied the complex dynamics of Saturn's rings, revealing them to be a dynamic, ever-changing system rather than the static bands they appear to be from Earth. The Cassini mission ended in 2017 with a planned plunge into Saturn's atmosphere to prevent any possibility of contaminating potentially habitable moons. But the data it returned will continue to yield new insights for decades to come, and future missions, like the Dragonfly rotorcraft to Titan, will build upon its discoveries. Beyond Saturn lie the ice giants, Uranus and Neptune. Uranus orbits at a distance of 2.9 billion kilometers from the Sun, while Neptune, the most distant major planet, circles our star at 4.5 billion kilometers. At these vast distances, light takes hours to travel between Earth and these worlds. The Voyager 2 spacecraft, launched in 1977, took 9 years to reach Uranus and 12 years to reach Neptune, the only spacecraft to visit these distant worlds up close. Despite the brief flyby encounters of Voyager 2, we learned that these ice giants are not simply smaller versions of Jupiter and Saturn, but represent a distinct class of planets with their own unique characteristics. Uranus, bizarrely, rotates on its side, with its axis of rotation nearly parallel to the plane of its orbit. Neptune hosts the fastest winds in the solar system, with speeds exceeding 2,000 kilometers per hour. Both planets have complex moon systems and faint ring systems not visible from Earth. No spacecraft has visited Uranus or Neptune since Voyager 2, making them the least explored major planets in our solar system. Future missions to these worlds would require either very long flight times or advanced propulsion technologies to reduce travel time. Yet these distant giants hold important clues about the formation and evolution of our solar system and about the nature of the many ice giant exoplanets that have been discovered orbiting other stars. But even the orbit of Neptune does not mark the edge of our solar system. Beyond the major planets lies the Kuiper Belt, a vast region populated by dwarf planets, including Pluto, and countless smaller icy bodies. The New Horizons spacecraft, which gave us our first close-up views of Pluto in 2015, took 9.5 years to reach its target, traveling at speeds of about 16 kilometers per second, nearly 60,000 kilometers per hour. The New Horizons flyby transformed our understanding of Pluto, revealing a complex and active world rather than the static, frozen body many had expected. With its large moon Charon and 4 smaller satellites, Pluto represents a binary system that provides insights into the dynamics of small bodies in the outer solar system. Its surface features, including the heart-shaped Tombor Regio, nitrogen ice glaciers, water ice mountains, and evidence of cryovolcanism, suggest a world with ongoing geological activity despite its small size and extreme distance from the Sun. Even at these tremendous speeds, the fastest ever achieved by a human-made object at launch, the journey to the outer solar system requires patience measured in years and decades. New Horizons continues to explore the Kuiper Belt, having flown past the object Arrokoth, formerly known as Ultima Thule, in 2019. As it ventures farther from Earth, communications with the spacecraft become increasingly delayed. Signals from New Horizons, traveling at the speed of light, now take several hours to reach Earth. The most distant human-made objects, however, are the Voyager probes. Launched in 1977, Voyagers 1 and 2 conducted a grand tour of the outer planets before heading toward interstellar space. Voyager 1 officially entered interstellar space in 2012, becoming the first human-made object to leave the protective bubble of our Sun's influence called the heliosphere. Voyager 2 followed in 2018. These remarkable spacecraft are now more than 20 billion kilometers from Earth. Signals from the Voyager probes take about 20 light hours to reach us. Despite being launched over 4 decades ago, they continue to function, sending back data about the environment at the boundary between our solar system and interstellar space. The Voyager probes have crossed the termination shock, where the solar wind slows from supersonic to subsonic speeds, and the heliosheath, the outermost layer of the heliosphere, where the solar wind is compressed and turbulent. They have now entered the interstellar medium, where the influence of other stars begins to exceed that of our Sun. This region represents the true boundary between our solar system and the rest of the galaxy. Yet even at their tremendous distances, the Voyager probes have traversed only a tiny fraction of the distance to the nearest star. Voyager 1, the faster of the 2 spacecraft, is traveling away from our solar system at about 17 kilometers per second. At this speed, it would take about 73,000 years to reach Proxima Centauri, if it were heading in that direction, which it is not. This sobering calculation illustrates the vast gulf between interplanetary travel, which humanity has achieved with robotic emissaries, and true interstellar travel, which remains beyond our current technological capabilities. The Voyager probes, traveling almost 1.5 million kilometers per day, would still require tens of thousands of years to reach even the closest star system. Beyond the Kuiper Belt lies the Oort cloud, a spherical shell of icy objects that surrounds our solar system at distances of up to 2 light-years from the Sun. This vast cloud, composed of billions or even trillions of comets and larger bodies, represents the outer boundary of our Sun's gravitational influence. No spacecraft has yet reached the Oort cloud, and none of our current or planned missions will do so within the operational lifetimes of their power sources and communications systems. The Oort cloud, named after the Dutch astronomer Jan Oort, who predicted its existence, is thought to be the source of long-period comets that occasionally visit the inner solar system. These icy travelers, with orbital periods measured in thousands or even millions of years, bring material from the outer reaches of our solar system into the warmth of the inner regions, where they develop tails and become visible from Earth. The vastness of the Oort cloud defies easy comprehension. While the Kuiper Belt is roughly disc-shaped, extending from about 30 astronomical units, the distance from Earth to the Sun, to about 50 astronomical units, the Oort cloud is a spherical shell extending from about 2,000 astronomical units to as much as 100,000 astronomical units, or about 1.6 light-years, from the Sun. At these distances, the Sun appears as just a particularly bright star, and its gravitational influence is so weak that objects in the outer Oort cloud are easily perturbed by passing stars or even the gravitational field of our galaxy. The space between the outer edge of the Oort cloud and the nearest stars represents the true interstellar void. This region is not empty, but is filled with a tenuous plasma known as the interstellar medium, permeated by magnetic fields, cosmic rays, and occasional clouds of gas and dust. The density of matter in this region is incredibly low, with an average of about 1 hydrogen atom per cubic centimeter. But over the vast distances between stars, this tenuous medium can still affect the journey of a spacecraft. To comprehend the true scale of these distances, imagine that our entire solar system, from the Sun out to the orbit of Neptune, was shrunk down to the size of a quarter, about 2.4 centimeters in diameter. On this scale, the nearest star, Proxima Centauri, would still be about 160 meters away. Our current most distant spacecraft would have traveled only about half a centimeter on this scale. The immensity of these distances has practical implications for how we explore space. Radio communications, traveling at the speed of light, already experience significant delays within our solar system. A round-trip radio message to Mars takes between 8 and 40 minutes, depending on the planet's relative positions. A round-trip message to the Voyager probes takes about 40 hours. A round-trip message to Proxima Centauri would take over 8 years. This means that any probe we send to another star would need to be almost entirely autonomous, capable of making decisions without real-time input from Earth. Moreover, the energy requirements for interstellar travel far exceed those of interplanetary journeys. The Voyager probes received gravity assists from the outer planets, using the gravitational pull of Jupiter, Saturn, and in the case of Voyager 2, Uranus and Neptune, to gain speed without expending fuel. These gravity assists were possible because of a rare alignment of the outer planets that occurs only once every 176 years. Even with these assists, the Voyager probes are traveling at speeds that would require tens of thousands of years to reach the nearest star. To reach the stars within a human lifetime, or even within a few generations, would require speeds hundreds or thousands of times faster than our current spacecraft can achieve. This is the propulsion problem, a challenge we will explore in more depth later in our journey. But before we contemplate the leap between stars, let us appreciate how far we have already come. In just over 60 years since the launch of Sputnik, humanity has extended its reach across the solar system. We have landed on the Moon, Mars, Venus, and Saturn's moon, Titan. We have orbited Jupiter, Saturn, and Mercury. We have flown past every major planet, and even dwarf planets and asteroids. We have touched a comet and returned samples from asteroid Bennu. We have sent spacecraft beyond the boundary of our Sun's protective magnetic bubble into true interstellar space. Each of these achievements represents a triumph of human ingenuity, perseverance, and cooperation. Each mission has pushed the boundaries of our technological capabilities and expanded our understanding of our cosmic neighborhood. Each success has built upon previous accomplishments, creating a foundation of knowledge and experience that brings us incrementally closer to the stars. Consider the Voyager probes, perhaps our greatest achievements in deep space exploration to date. Designed in the 1970s with computers less powerful than a modern smartphone, these spacecraft have operated for over 4 decades in the harsh environment of space. They have survived radiation, micrometeoroid impacts, and the extreme cold of the outer solar system. They have returned data that has revolutionized our understanding of the gas giants and the boundary between our solar system and interstellar space. The Voyager probes carry with them the golden records, phonograph records containing sounds and images selected to portray the diversity of life and culture on Earth. These records were intended as a message to any extraterrestrial civilization that might one day find the spacecraft, a cosmic greeting card from humanity. Though the probability of such a discovery is vanishingly small, the golden records represent an important symbolic gesture, an acknowledgement that the Voyager probes are not merely scientific instruments, but ambassadors of humanity to the cosmos. The New Horizons mission to Pluto has similarly pushed the boundaries of our exploration capabilities. Launched in 2006, it became the fastest spacecraft ever to leave Earth orbit, yet still took 9.5 years to reach Pluto. The images it returned transformed our understanding of this distant world, revealing a surprisingly active surface with mountains of water ice, glaciers of nitrogen ice, and a thin atmosphere. What was once thought to be a static, frigid world at the edge of our solar system turned out to be a complex, dynamic place with its own unique geology and weather. The success of these missions demonstrates the remarkable capabilities of robotic explorers. Equipped with sophisticated instruments and powered by radioisotope thermoelectric generators, which convert the heat from decaying plutonium into electricity, these spacecraft can operate for decades in the most extreme environments. They can survive the intense radiation belts of Jupiter, the frigid darkness of the outer solar system, and the vacuum of interstellar space. But these missions also highlight the limitations of our current capabilities. The vast distances involved mean that exploration takes patience. The New Horizons flyby of Pluto lasted only a few hours, after a journey of nearly a decade. The data collected during this brief encounter took months to transmit back to Earth due to the limited power available for the spacecraft's radio transmitter and the immense distance the signals had to travel. The challenges of interplanetary travel, significant as they are, pale in comparison to the hurdles of interstellar journeys. Yet the lessons learned from our solar system exploration provide valuable insights that will inform our efforts to reach the stars. The reliability and longevity of the Voyager probes demonstrate that we can build spacecraft capable of operating for decades. The success of complex maneuvers like gravity assists shows that we can navigate the intricacies of orbital mechanics to maximize efficiency. The autonomy of probes like New Horizons, operating at distances where real-time control from Earth is impossible, points the way toward the even greater autonomy that interstellar probes would require. As we continue our current explorations of the solar system, with missions like the Europa Clipper to investigate Jupiter's potentially habitable moon, the Dragonfly rotorcraft to explore Saturn's moon Titan, and various rovers and sample return missions to Mars, we are not only learning about our planetary neighbors, but also developing technologies and expertise that bring us incrementally closer to the stars. Each mission pushes the boundaries of what we can achieve, extending our reach farther into the solar system and developing technologies that make spacecraft more capable, more reliable, and more efficient. Each discovery deepens our understanding of the cosmos and fuels our desire to explore further. The path from Earth to the edge of our solar system has been one of incremental progress, of small steps that, taken together, represent a giant leap in our capabilities as a spacefaring species. The journey to the stars will follow a similar trajectory, built upon the accumulated knowledge and technological advancement of generations of explorers and engineers. The story of our exploration of the solar system is not merely a chronology of missions and discoveries, but a testament to the human spirit of exploration and discovery. It is a story of overcoming challenges, of learning from failures, of international cooperation transcending political boundaries, and of the wonder and awe that drive us to look beyond our own world. When we look back at Earth from the vantage point of the outer solar system, as the Voyager 1 spacecraft did in 1990, capturing the famous pale blue dot image, we gain a new perspective on our place in the cosmos. Carl Sagan eloquently described this image. Look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. This perspective, gained through our exploration of the solar system, reminds us of both the preciousness of our home planet and the vastness of the cosmos that awaits our exploration. As we stand at the edge of our solar system, looking outward toward the stars, we must acknowledge both how far we have come and how far we have yet to go. The distance between Neptune and Proxima Centauri is approximately 10,000 times greater than the distance between the Sun and Neptune. The void between stars is not merely empty space, but a region of extremely low-density plasma, known as the interstellar medium, permeated by cosmic rays, magnetic fields, and occasional clouds of gas and dust. This is the vast gulf we must somehow cross if we are to reach even our nearest stellar neighbors. Yet as daunting as this challenge may seem, it is not insurmountable. Just as the challenges of reaching the Moon or Mars once seemed beyond our capabilities, the stars may come within our grasp through sustained effort, technological innovation, and the uniquely human qualities of curiosity, ingenuity, and determination. So as we conclude our survey of humanity's journey from Earth to the edge of our solar system, let us carry forward the lessons learned from these explorations. Let us appreciate the remarkable achievements of our robotic emissaries while acknowledging the limitations of our current capabilities. And let us look toward the stars, not with despair at their remoteness, but with hope that they, too, may one day feel the touch of human curiosity, carried by spacecraft more advanced than any we can currently imagine. The edge of our solar system is not the end of our journey, but merely the beginning of a new and greater adventure, one that will challenge us to push the boundaries of our technology, our patience, and our imagination. Beyond the orbit of Neptune, beyond the Kuiper Belt, beyond the Oort cloud, lie the stars, waiting to be explored. As we venture beyond the boundaries of our solar system, we encounter the vast interstellar void that separates us from our stellar neighbors. In this chapter, we will explore the star systems closest to our Sun, examining their properties, their planets, and the challenges and opportunities they present for humanity's first interstellar voyages. Our nearest stellar neighbor is the Alpha Centauri system, a triple star system located approximately 4.37 light-years from Earth. This distance, while vast by human standards, represents our closest opportunity to explore another star system. The light we see from Alpha Centauri today began its journey toward Earth in late 2020 or early 2021. In the cosmic neighborhood, these stars are practically our next-door neighbors. The Alpha Centauri system consists of 3 stars. Alpha Centauri A and B are similar to our Sun, forming a binary pair that orbit around each other. Alpha Centauri A is slightly larger and brighter than our Sun, a G-type star with about 1.1 times the mass of our Sun and 1.5 times its luminosity. Alpha Centauri B is somewhat smaller and dimmer, a K-type star with about 0.9 times the mass of our Sun and about half its luminosity. These 2 stars orbit each other relatively closely, with an average separation of about 23 astronomical units, similar to the distance between our Sun and Uranus. They complete one orbit around their common center of mass every 80 years. The third member of the system, Proxima Centauri, is a small, dim red dwarf star orbiting much farther out from the main pair. Proxima is about 1/8 the mass of our Sun and emits only about 1/700th of the Sun's energy. It orbits the Alpha Centauri A and B pair at a distance of about 13,000 astronomical units, completing one orbit in roughly 550,000 years. Despite its dimness, Proxima Centauri holds special significance for us because it is currently the closest star to our Sun, at a distance of about 4.24 light-years. The Alpha Centauri system has captivated human imagination for centuries. It appears as a single bright star to the naked eye, visible primarily from the southern hemisphere of Earth. In fact, it is the 3rd brightest star in our night sky, after Sirius and Canopus. To ancient observers in the southern hemisphere, Alpha Centauri served as an important navigational beacon. The indigenous peoples of Australia incorporated it into their celestial mythology, and European explorers used it to guide their ships through southern waters. Modern astronomical observations have revealed the Alpha Centauri system in much greater detail, transforming it from a distant point of light into a complex stellar system with its own unique characteristics. The binary nature of Alpha Centauri A and B was discovered in 1839 by Thomas Henderson, a Scottish astronomer who also made the first accurate measurement of its distance from Earth using the stellar parallax method. Proxima Centauri was discovered much later, in 1915, by the Scottish astronomer Robert Innes. Its proximity to our solar system was not immediately recognized, and it was only after careful measurements of its proper motion and parallax that astronomers confirmed it was indeed the closest star to our Sun. Despite being part of the Alpha Centauri system, Proxima is not visible to the naked eye due to its intrinsic dimness. In recent years, the Alpha Centauri system has become even more intriguing with the discovery of exoplanets orbiting Proxima Centauri. In 2016, astronomers announced the detection of Proxima Centauri b, a rocky planet orbiting within the habitable zone of its parent star. This discovery sent waves of excitement through the scientific community and the public alike. For the first time, we had confirmed the existence of a potentially habitable world around the very nearest star to our Sun. Proxima Centauri b orbits its star at a distance of only about 7.5 million kilometers, completing one orbit in just 11.2 Earth days. Despite this close proximity to its star, the planet receives about the same amount of energy as Earth does from the Sun, because Proxima Centauri is so much dimmer than our Sun. This places the planet within the habitable zone, the region around a star where temperatures might allow for liquid water to exist on a planet's surface. Proxima b is estimated to have a minimum mass of about 1.27 times that of Earth, suggesting it is a rocky world rather than a gas giant like Jupiter or Saturn. However, its close orbit around Proxima Centauri presents both opportunities and challenges for potential habitability. On one hand, the energy input from the star could support Earth-like temperatures. On the other hand, Proxima Centauri is a highly active star, emitting powerful flares that could strip away any atmosphere and bathe the planet's surface in deadly radiation. In 2020, astronomers announced the discovery of a second planet, Proxima Centauri c, a gas giant orbiting much farther out from the star. This planet has an estimated mass about 7 times that of Earth and orbits at a distance of about 1.5 astronomical units from Proxima Centauri, completing one orbit in about 5 years. At this distance, the planet is too cold for liquid water and is unlikely to be habitable in any Earth-like sense. The discovery of these planets around our nearest stellar neighbor has profound implications for our understanding of planetary systems and for the potential of finding habitable worlds beyond our solar system. If a potentially habitable planet exists around the very nearest star to our Sun, then such worlds may be common throughout our galaxy. The main pair, Alpha Centauri A and B, have also been the subject of intense planet hunting efforts. In 2012, astronomers announced the discovery of a planet orbiting Alpha Centauri b, but this claim was later retracted when further analysis showed the signal was likely an artifact of the data analysis method. As of today, no confirmed planets have been detected around either Alpha Centauri A or B, but the search continues with ever more sensitive instruments. The Alpha Centauri system represents our best first target for interstellar exploration. Its proximity means that a probe sent from Earth would reach it sooner than any other star system. The presence of multiple stars within a single system offers the opportunity to study different stellar types in one mission, and the existence of at least one potentially habitable planet makes it a compelling destination for astrobiological studies. But even at this relatively close distance, reaching Alpha Centauri with current technology would be an extraordinary challenge. The Voyager 1 spacecraft, currently the fastest human-made object to leave our solar system, is traveling at about 17 kilometers per second relative to the Sun. At this speed, it would take about 75,000 years to reach Alpha Centauri. Clearly, new propulsion technologies would be needed to make such a journey within a time frame relevant to human civilization. Moving outward from Alpha Centauri, our next nearest stellar neighbor is Barnard's star, a red dwarf located about 6 light-years from our solar system. Discovered in 1916 by the American astronomer Edward Emerson Barnard, this star is notable for having the highest proper motion of any known star. It appears to move across our sky more rapidly than any other star, changing its position by about 10.3 arc-seconds per year. This rapid apparent motion is due to a combination of its proximity to us and its high velocity relative to our solar system. Barnard's star is smaller and dimmer than even Proxima Centauri, with about 14% of the Sun's mass and only about 4/1000ths of its luminosity. Like many red dwarfs, it is extremely long-lived, with an estimated age of about 10 billion years, roughly twice the age of our Sun. It will continue to shine for trillions of years more, long after our Sun has exhausted its nuclear fuel. In 2018, astronomers announced the discovery of a planet orbiting Barnard's star. Designated Barnard's star B, this world has a mass of at least 3.2 times that of Earth and orbits at a distance similar to Mercury's orbit around our Sun. Despite this relatively close orbit, the planet receives only about 2% of the energy that Earth receives from the Sun, making its surface likely frozen. with an estimated temperature of about -170 degrees Celsius. The discovery of a planet around Barnard's star was the culmination of a search that began in the 1960s, when astronomer Peter van der Kamp claimed to have detected a Jupiter-sized planet based on wobbles in the star's position. These claims were later refuted, and it took modern precision instruments to finally confirm the existence of a planet around this neighboring star. Continuing our tour of the nearby stellar neighborhood, we encounter another red dwarf, Wolf 359, located about 7.9 light-years from our solar system. This star, discovered in 1919 by the German astronomer Max Wolf, is one of the smallest and faintest stars known. It has only about 8% of the Sun's mass and emits merely about 1/16,000th of the Sun's energy. Despite its intrinsic dimness, Wolf 359 gained fame in popular culture through its mention in science fiction, most notably in Star Trek, where it is the location of a Federation of Planets outpost. In reality, while no planets have been confirmed around Wolf 359, it remains a target of interest for exoplanet hunters due to its proximity to our solar system. At a similar distance of about 8.3 light-years lies Lalande 21185, yet another red dwarf star. This star has about half the mass of our Sun and about 2.7% of its luminosity. It was catalogued by the French astronomer Jérôme Lalande in 1799, though its proximity to our solar system was not recognized until much later. In 2019, astronomers announced the discovery of a planet orbiting Lalande 21185. This world, with a mass of about 3 times that of Earth, orbits within the habitable zone of its star, making it another potentially interesting target for studies of habitability. However, like many planets around red dwarf stars, it likely faces challenges from stellar flares and tidal locking, where the same side of the planet always faces the star. At about 8.6 light-years from Earth, we find the Sirius system, the brightest star in our night sky. Sirius is actually a binary system, consisting of Sirius A, a main sequence star about twice the mass of our Sun and 25 times as luminous, and Sirius B, a white dwarf companion that was once a larger star, but has since shed its outer layers, leaving behind a dense core about the size of Earth but with a mass comparable to our Sun. The Sirius system has played an important role in human culture throughout history. Ancient Egyptians used the heliacal rising of Sirius, its first appearance in the dawn sky after a period of invisibility, to predict the annual flooding of the Nile River. Many other cultures incorporated Sirius into their mythologies and calendars due to its prominent position in the night sky. Despite its brightness in our sky, Sirius is not a likely candidate for detecting habitable planets. Sirius A is a relatively young star, only about 240 million years old, which is less than 6% of the age of our Sun. This youth means that even if planets exist around Sirius A, they would not have had enough time to develop complex life as we know it on Earth. Additionally, the presence of Sirius B complicates the gravitational environment of the system, potentially disrupting stable planetary orbits in the habitable zone. Moving slightly farther out, at a distance of about 10.7 light-years, we encounter Epsilon Eridani, a star more similar to our Sun than many of our closer neighbors. Epsilon Eridani is a K-type main sequence star with about 82% of the Sun's mass and about 1/3 of its luminosity. It is a young star, only about 600 million years old, still in the early stages of its life cycle. Epsilon Eridani has been of particular interest to astronomers and science fiction authors alike because of its similarity to our Sun and its proximity to our solar system. It was one of the first targets of Project Ozma in 1960, an early scientific search for extraterrestrial intelligence that used radio telescopes to listen for artificial signals from nearby stars. In 2000, astronomers announced the discovery of a Jupiter-sized planet orbiting Epsilon Eridani at a distance similar to Jupiter's orbit around our Sun. This discovery, along with subsequent observations of a debris disk around the star similar to our solar system's Kuiper belt, suggests that Epsilon Eridani may host a planetary system analogous to our own, though at a much earlier stage of development. At about 11 light-years from Earth lies Tau Ceti, another star similar to our Sun. Tau Ceti is a G-type main sequence star with about 78% of the Sun's mass and about 55% of its luminosity. It is one of the most stable and inactive stars known, with little variation in its energy output over time. This stability, combined with its similarity to our Sun, makes Tau Ceti a prime target in the search for habitable exoplanets. In 2017, astronomers announced the discovery of 4 planets orbiting Tau Ceti, including 2 that may lie within the star's habitable zone. These planets have masses between about 1.7 and about 4 times that of Earth, placing them in the super-Earth category. However, Tau Ceti also possesses a substantial debris disk, containing about 10 times as much material as our Sun's asteroid belt. This abundance of potentially impacting objects could present challenges for the development of life on any planets in the system, as frequent large impacts might disrupt evolutionary processes. Moving along to a distance of about 11.4 light-years from Earth, we encounter Ross 154, yet another red dwarf star. This star has only about 17% of the Sun's mass and about 5/1000ths of its luminosity. It gained scientific attention in 2017 with the announcement of a potentially habitable planet, Ross 154b, orbiting within the star's habitable zone. Ross 154b is estimated to have a mass of about 1.4 times that of Earth and receives about 65% of the energy that Earth receives from the Sun. This places it well within the habitable zone, making it one of the most promising nearby candidates for a world that could support liquid water on its surface. At a distance of about 11.9 light-years from our solar system lies Procyon, a binary system consisting of Procyon A, a white to yellow main sequence star, about 1.5 times the mass of our Sun, and 7 times as luminous, and Procyon B, a white dwarf companion. Procyon is the 8th brightest star in our night sky and has been known since ancient times, featuring in various mythologies and celestial navigation systems. No planets have yet been confirmed around either component of the Procyon system, but its proximity to Earth ensures that it remains a target of interest for exoplanet hunters. The binary nature of the system and the different evolutionary stages of its 2 stars make it a valuable laboratory for studying stellar evolution and the interactions between stars at different phases of their life cycles. These star systems, all within about 12 light-years of our solar system, represent our immediate cosmic neighborhood. They are the stars that would be our first stepping stones as we venture beyond our solar system, the first ports of call on humanity's journey to the stars. But even these nearest stars are separated from us by distances that challenge our current technological capabilities. To better understand the scale of our cosmic neighborhood, let us consider the light year, our standard unit of measurement for interstellar distances. A light year is the distance that light, traveling at the fastest speed physically possible, covers in 1 Earth year. Light travels at approximately 299,792,458 meters per second in a vacuum. In 1 year, it covers a distance of about 9.46 trillion kilometers. To put this in perspective, light from the Sun takes about 8 minutes to reach Earth. Light from Proxima Centauri, our nearest stellar neighbor, takes about 4.24 years to reach us. This means that when we observe Proxima Centauri, we are seeing it as it was over 4 years ago, not as it is right now. These vast distances have profound implications for interstellar exploration. Even if we could build a spacecraft capable of traveling at 1/10 the speed of light, a velocity far beyond our current technological capabilities, it would still take over 40 years to reach Proxima Centauri. This is longer than many human careers and approaches the length of a typical human generation. The challenge of distance is compounded by the energy requirements for interstellar travel. To accelerate a spacecraft to a significant fraction of the speed of light would require enormous amounts of energy. For example, to accelerate a spacecraft with a mass of 1,000 kilograms to 10% of the speed of light would require about 4.5 times 10 to the 17 joules of energy, equivalent to the total energy consumption of human civilization for several years. Moreover, once a spacecraft reaches its destination, it would need to decelerate to enter orbit around a target star or planet, which would require comparable amounts of energy. Traditional rocket propulsion, which relies on carrying both fuel and oxidizer, becomes impractical for such missions due to the exponential relationship between delta V, the change in velocity, and the mass ratio of the spacecraft, described by the Tsiolkovsky rocket equation. Despite these challenges, the nearest star systems offer compelling targets for humanity's first ventures beyond our solar system. Proxima Centauri b, the potentially habitable world around our closest stellar neighbor, represents an opportunity to study an Earth-sized planet outside our solar system up close. The Alpha Centauri system as a whole, with its 3 different types of stars, offers a natural laboratory for studying stellar properties and evolution. Barnard's star, with its super-Earth planet orbiting in a frigid environment, provides an opportunity to study planetary formation and evolution in conditions very different from those in our inner solar system. The potentially habitable worlds around Ross 154 and Lalande 21185 offer additional targets for comparative planetology and the search for signs of life beyond Earth. Even the stars without confirmed planets, like Wolf 359, remain valuable targets for exploration. The absence of detected planets does not necessarily mean an absence of worlds altogether, as current detection methods are biased toward finding large planets in certain types of orbits. Smaller worlds, similar in size to Earth, could exist around these stars and simply remain undetected with current technology. Furthermore, the interstellar medium itself, the tenuous gas and dust that fills the space between stars, is worthy of scientific study. The properties of this medium, including its density, composition, and the strength and orientation of magnetic fields within it, are difficult to measure from within our solar system. A probe traveling through this medium could make direct measurements that would inform our understanding of the structure and evolution of our galaxy. As we contemplate the nearest star systems as potential destinations for interstellar missions, we must also consider the timescales involved. Even with significant advances in propulsion technology, journeys to these stars would likely take decades or centuries. This means that the scientists and engineers who design and launch an interstellar mission may not live to see its arrival at its destination. The data returned by such a mission might be received by a generation that was not yet born when the mission began. This temporal disconnect presents unique challenges for mission planning and institutional continuity. How do we ensure that the knowledge and expertise needed to receive and interpret data from an interstellar probe are maintained over the course of decades or centuries? How do we design spacecraft that can operate reliably for such extended periods without maintenance or repair? These questions will be central to the planning of any serious interstellar mission. Despite these challenges, the nearest star systems beckon us with promises of discovery and the potential expansion of human understanding beyond the confines of our solar system. They represent the next great threshold in our exploration of the cosmos, a threshold that will require us to develop new technologies, new institutional structures, and perhaps new ways of thinking about ourselves and our place in the universe. The stars closest to our solar system are not merely points of light in our night sky, but unique stellar systems with their own characteristic properties, planetary companions, and potential for discovery. As we continue to study these nearby stars with ever more powerful telescopes and detectors, we gain deeper insights into the diversity and complexity of stellar and planetary systems in our cosmic neighborhood. Recent technological advances have dramatically expanded our knowledge of these nearby stars and their planetary systems. The TESS, or Transiting Exoplanet Survey Satellite, mission, launched in 2018, has been surveying the nearest and brightest stars for evidence of transiting exoplanets. The Gaia Space Observatory, launched in 2013, has been mapping the positions and motions of billions of stars with unprecedented precision, refining our understanding of the three-dimensional structure of our stellar neighborhood. Ground-based observation programs, such as the Espresso spectrograph on the Very Large Telescope in Chile, have achieved the sensitivity necessary to detect Earth-sized planets around nearby stars. The combination of these space and ground-based observations has revealed our stellar neighborhood to be rich with worlds, many of which lie within the habitable zones of their parent stars. As we look to the future, new observatories like the James Webb Space Telescope, a joint project of NASA, ESA, and the Canadian Space Agency, will allow us to study the atmospheres of exoplanets around nearby stars. This capability may allow us to detect signs of life, such as the presence of oxygen, methane, or other biosignature gases, in the atmospheres of these worlds. The nearest star systems, within about 20 light-years of our solar system, include more than 50 known stars. The majority of these are red dwarfs, smaller and dimmer than our Sun but far more common in our galaxy. Others include stars similar to our Sun, binary and multiple star systems, and white dwarfs, the dense remnants of stars that have exhausted their nuclear fuel. This diverse collection of stellar neighbors represents a microcosm of our galaxy as a whole. By studying these nearest stars and their planetary systems in detail, we gain insights into the processes of star and planet formation, stellar evolution, and potentially the conditions necessary for the emergence and sustenance of life. The stars closest to our solar system also represent the most logical first targets for any future interstellar missions. Their proximity means that the travel time, while still measured in decades with foreseeable technology, would be shorter than for more distant targets. The diversity of stellar types and planetary systems within this nearby volume of space ensures that even a small number of missions could yield a wealth of comparative data. Moreover, the nearest stars are distributed in all directions around our solar system, forming a roughly spherical volume with the Sun at its center. This means that initial interstellar missions could be sent in multiple directions, maximizing the diversity of environments explored while minimizing the maximum travel distance for any single mission. The study of our nearest stellar neighbors also has philosophical and cultural implications. As we learn more about these nearby worlds, we gain perspective on our own planet and its place in the cosmos. The discovery of potentially habitable worlds around nearby stars raises profound questions about whether we are alone in the universe or whether life, perhaps even intelligent life, might exist within just a few light years of Earth. Even more fundamentally, the study of nearby stars and their planets helps us understand our own origins. The elements that make up our planet and our bodies were forged in the hearts of stars that lived and died before our sun was born. As we study the nearest stars, we are studying systems that, while separate from our own, are part of the same galactic ecosystem that gave rise to our solar system and ultimately to us. This connection to the nearest stars is not merely scientific but also aesthetic and emotional. Looking up at the night sky, knowing that those points of light represent other suns, many with their own families of planets, inspires a sense of wonder and possibility that transcends cultural and historical boundaries. The nearest stars have inspired poetry, art, music, and literature across human history, serving as beacons of imagination and aspiration. As we prepare to take our first tentative steps beyond our solar system, perhaps first with robotic probes and eventually with human missions, the nearest stars will serve as both physical destinations and symbolic waypoints on humanity's journey to the cosmos. They are the first stops on a voyage that may ultimately take us throughout our galaxy and perhaps beyond. A voyage that will require not only technological innovation, but also cultural adaptation and a long-term perspective that spans generations. The nearest star systems, with their unique characteristics and their relative proximity to Earth, represent the beginning of interstellar space, the vast frontier that extends beyond the influence of our Sun. They are close enough to be studied with current and near-future technology, yet far enough away to challenge our capabilities and imagination. They are, in many ways, the perfect next step in humanity's ongoing journey of exploration and discovery. As we gaze at these stars in our night sky, may we remember that the light we see began its journey years ago, crossing the interstellar void to reach our eyes. In that time, life on Earth has continued to evolve and change, and human civilization has continued to develop new technologies and new understanding. Perhaps someday, we will send emissaries of our own to follow that light back to its source, carrying the accumulated knowledge and aspirations of humanity to new worlds around other suns. The stars are waiting. They have been there for billions of years, and they will remain for billions more. The question is not whether they will wait for us, but whether we will rise to the challenge they present, developing the technologies and the cultural institutions necessary to reach them. The nearest stars are not merely objects of scientific study, but a test of our capabilities and our commitment to exploration. As we conclude our tour of the nearest star systems, let us carry with us the knowledge that these distant suns are not merely points of light in our night sky, but complex stellar systems with their own unique characteristics and planetary companions. They are our cosmic neighbors, separated from us by vast but not insurmountable distances, and perhaps someday They will be the sites of humanity's first tentative steps into the broader galactic community. The nearest stars beckon. The journey will be long and challenging, but the rewards of discovery and expanded understanding make it a journey worth undertaking. As we look toward the stars, we look toward our future as a spacefaring species, a future that begins with our nearest stellar neighbors, but extends to the farthest reaches of our galaxy and beyond. As we contemplate voyages to even our nearest stellar neighbors, we must confront the sobering reality of interstellar distances. The void between stars presents obstacles of such magnitude that they transcend typical human experience. These challenges go far beyond the merely technical concerns of propulsion or spacecraft design. They reach into the domains of time, energy, communication, and even human psychology. In this chapter, we will explore these challenges in depth, examining what it truly means to traverse the vast gulfs that separate our solar system from other stars. The most fundamental challenge of interstellar travel is, of course, the sheer distance involved. Even Proxima Centauri, our nearest stellar neighbor, lies more than 4 light-years away from Earth. To grasp the immensity of this distance, consider that light, traveling at nearly 300,000 kilometers per second, takes more than 4 years to make the journey. Our fastest current spacecraft, by comparison, would require tens of thousands of years to reach this relatively close star. The New Horizons probe, which flew past Pluto in 2015, is traveling at about 16 kilometers per second relative to the Sun. At this speed, it would take approximately 80,000 years to reach Proxima Centauri. The Voyager spacecraft, our most distant human-made objects, are moving at similar speeds and would require comparable timeframes to reach the nearest stars if they were heading in those directions, which they are not. This vast disparity between the distances we wish to traverse and the speeds we can currently achieve illustrates the first major challenge of interstellar travel. We must develop propulsion technologies capable of speeds far beyond our current capabilities. To bring interstellar journeys within timeframes relevant to human civilization, perhaps decades or at most centuries, we would need to achieve speeds of at least 1% of the speed of light, or about 3,000 kilometers per second. This is roughly 200 times faster than our current fastest spacecraft. Achieving such speeds presents enormous engineering challenges. Traditional chemical rockets, which rely on the energy released by chemical reactions between fuel and oxidizer, are fundamentally limited by the energy density of chemical bonds. Even the most energetic chemical reactions release only a tiny fraction of the energy needed to accelerate a spacecraft to a significant fraction of the speed of light. Moreover, the rocket equation, first derived by Konstantin Tsiolkovsky in 1903, imposes a harsh reality. As the desired change in velocity increases, the ratio of initial mass, including fuel, to final mass grows exponentially. For the velocities needed for reasonable interstellar travel times, this ratio becomes so large that chemical propulsion becomes completely impractical. A rocket carrying enough chemical fuel to reach even 1% of the speed of light would be almost all fuel, with virtually no room for payload. Alternative propulsion technologies, such as nuclear fission, nuclear fusion, or even antimatter reactions, offer higher energy densities, but present their own technological challenges. Developing these technologies to the point where they could power interstellar journeys is a task that may require decades or centuries of focused research and development. Even if we could develop propulsion systems capable of accelerating spacecraft to a significant fraction of the speed of light, we would still face the challenge of deceleration. A probe passing through a star system at high speed would have little time to make observations or transmit data back to Earth. To conduct meaningful exploration, the spacecraft would need to slow down, which would require carrying even more fuel or developing some method of using resources in the target star system for deceleration. The time required for interstellar journeys presents another set of profound challenges. Even at 1/10 the speed of light, a journey to Proxima Centauri would take more than 40 years. This time frame exceeds the typical duration of a human career and approaches the length of a human generation. A mission to a star 10 light-years away would take a century at this speed, longer than a typical human lifespan. These extended timeframes have significant implications for mission planning, spacecraft design, and the psychological and sociological aspects of interstellar travel. A spacecraft designed for a journey of decades or centuries must be extraordinarily reliable, capable of operating without maintenance or repair for periods far exceeding the operational lifetimes of our current space hardware. The Voyager probes, launched in 1977, have operated for over 4 decades, a remarkable achievement, but still far short of the timeframes required for interstellar missions. Creating systems that can function reliably for centuries would require not only advances in materials science and engineering, but also new approaches to redundancy, self-repair, and autonomous operation. The extended duration of interstellar journeys also raises questions about institutional continuity and knowledge transfer. The scientists and engineers who design and launch an interstellar mission would likely not be the ones who receive and analyze the data it returns. This temporal disconnect requires robust mechanisms for preserving knowledge and maintaining commitment to the mission across multiple human generations. For missions involving human crews, the time challenge becomes even more acute. A one-way journey of many decades or centuries would span multiple human lifetimes, requiring either some form of suspended animation technology, currently the stuff of science fiction, or the establishment of generation ships, self-contained habitats where people would live, reproduce, and die during the course of the journey, with only their descendants arriving at the destination. Generation ships present their own complex challenges, including the need to maintain a stable, closed ecological system for centuries, to provide for the physical and psychological well-being of multiple generations of travelers, and to ensure the continuity of the mission's purpose and technical knowledge across generations. The social dynamics of such isolated, confined communities over extended periods would likely be complex and potentially problematic. An alternative to generation ships might be the development of suspended animation or hibernation technologies that could place human travelers in a state of drastically reduced metabolic activity for the duration of the journey. While such technologies have been a staple of science fiction for decades, they remain largely speculative from a scientific perspective. Some promising research has been conducted on induced hypothermia and oxygen deprivation tolerance in mammals, but we are still very far from being able to safely pause and restart human life for periods of decades. The third major challenge of interstellar travel is the energy requirement. The kinetic energy of a moving object increases with the square of its velocity. This means that to achieve speeds of a significant fraction of the speed of light requires enormous amounts of energy. To accelerate a spacecraft with a mass of 1,000 kilograms to 10% of the speed of light would require about 4.5 times 10 to the 17th joules of energy, equivalent to the total energy consumption of human civilization for several years. Generating, storing, and efficiently utilizing such vast amounts of energy presents technological challenges far beyond our current capabilities. Even nuclear energy, both fission and fusion, while offering much higher energy densities than chemical reactions, would require enormous quantities of fuel to achieve interstellar velocities for spacecraft of meaningful size. Antimatter, with its perfect conversion of mass to energy according to Einstein's famous equation, E=mc², offers the highest theoretical energy density of any known fuel. However, antimatter is incredibly difficult and energy-intensive to produce with current technology. The entire world's production of antimatter to date amounts to only nanograms, and it costs billions of dollars per gram to produce. Moreover, storing antimatter presents its own challenges, as it annihilates upon contact with normal matter, requiring complex electromagnetic containment systems. Beyond the challenges of propulsion, time, and energy, interstellar missions must also overcome the obstacles presented by the interstellar medium itself. While space is often described as a vacuum, the regions between stars are not truly empty. They contain a tenuous plasma of hydrogen and helium, with an average density of about 1 atom per cubic centimeter, as well as dust particles, cosmic rays, and magnetic fields. At the high velocities required for practical interstellar travel, even this sparse medium can cause significant damage to a spacecraft. A vessel traveling at 10% of the speed of light would impact interstellar hydrogen atoms with energies of about 4.7 mega-electron volts, sufficient to cause nuclear reactions and significant radiation damage to the spacecraft's structure and systems over time. Dust particles, though rare in the interstellar medium, present an even greater hazard. A collision with a dust grain 1 micrometer in diameter at 10% of the speed of light would release energy equivalent to about 7 kilograms of TNT, potentially causing catastrophic damage to an unprotected spacecraft. Some form of shielding or deflection system would be essential for any interstellar mission, adding mass and complexity to the spacecraft design. Cosmic rays, high-energy particles primarily from sources outside our solar system, present a radiation hazard to both electronic systems and potential human crews. The long duration of interstellar journeys would result in cumulative radiation doses far exceeding those experienced in any previous human space mission, necessitating robust radiation shielding or other protective measures. Communication across interstellar distances presents yet another set of challenges. Radio waves, like light, travel at the speed of light, meaning that a transmission from a probe at Proxima Centauri would take more than 4 years to reach Earth. A response from Earth would take another 4+ years to reach the probe, resulting in a round-trip communication delay of more than 8 years. This extended communication delay makes real-time control of an interstellar probe from Earth completely impractical. Any interstellar mission would need to be largely autonomous, capable of making decisions and solving problems without real-time input from human controllers. While artificial intelligence has advanced significantly in recent decades, creating systems capable of operating independently for decades or centuries in the unpredictable environment of interstellar space remains a formidable challenge. The bandwidth of communications across interstellar distances would also be severely limited by the inverse square law, which states that the intensity of a signal decreases with the square of the distance from the source. A radio transmitter that provides a strong signal within our solar system would produce a signal billions of times weaker at the distance of even the nearest stars. This signal attenuation would limit the rate at which data could be transmitted back to Earth, potentially restricting the scientific return of the mission. Laser communication systems, which use tightly focused beams of light to transmit information, offer potential advantages over radio in terms of data rate and power efficiency for interstellar communications. However, they require precise pointing over enormous distances and are subject to the same speed of light delay as radio signals. The isolation of interstellar space presents psychological challenges as well. For robotic missions, the vast distances involved mean operating without real-time control or feedback from Earth for extended periods. For human missions, the psychological impact of being farther from Earth than any humans have ever traveled, with no possibility of timely assistance or return in case of emergency, would be profound. As a spacecraft journeys away from our solar system, Earth would gradually diminish to a pale dot in the cosmic darkness and eventually become indistinguishable from other stars. The awareness of being truly alone in the interstellar void, with Earth and all of human civilization unreachable for decades or centuries, could have significant psychological effects on human travelers. Studies of isolated, confined environments on Earth, such as Antarctic research stations, submarines, and space station missions, provide some insights into the psychological challenges of long-duration space missions. However, these environments all share a common factor that would be absent in interstellar travel: the knowledge that help is available within a relatively short time if needed. The true isolation of interstellar space would be unprecedented in human experience. Maintenance and reliability over extended timeframes present additional technical challenges. No human-made machine has ever operated continuously for the decades or centuries that would be required for interstellar missions. Current spacecraft typically include redundant systems for critical functions, but even with redundancy, the probability of system failure increases over time. For robotic missions lasting decades or centuries, some form of self-repair capability would likely be essential. This might involve robotic systems capable of diagnosing and fixing problems, modular designs that allow for the isolation and replacement of failed components, or even biomimetic systems that can heal damage in a manner similar to living organisms. All of these approaches are in their infancy as technologies and would require significant advancement before they could be relied upon for interstellar missions. For human missions, the need for reliable life support systems adds another layer of complexity. A closed ecological system capable of sustaining human life for decades or centuries without external resupply would need to recycle air, water, and nutrients with near-perfect efficiency. Any significant loss of resources over time would require carrying additional supplies, increasing the mass of the spacecraft and the energy required for propulsion. The challenge of reliability extends to the human component of interstellar missions as well. The health and well-being of human travelers over extended periods in the space environment is a subject of ongoing research. Current data from missions on the International Space Station have shown that microgravity causes significant physiological changes, including bone and muscle loss, cardiovascular deconditioning, immune system alterations, and vision problems. While countermeasures such as exercise and medication can mitigate some of these effects, the long-term implications of years or decades in microgravity remain uncertain. For interstellar journeys, some form of artificial gravity, likely created by rotation of all or part of the spacecraft, might be necessary to maintain human health over extended periods. The radiation environment of interstellar space presents additional health challenges. Beyond the protective bubble of Earth's magnetic field and atmosphere, cosmic radiation can cause cellular damage, increasing the risk of cancer and other diseases. The radiation dose accumulated during a journey of decades or centuries could exceed safe limits, necessitating substantial shielding or other protective measures. Reproduction and child development in the space environment represent largely unexplored territories. For generation ships, the ability of humans to conceive, bear, and raise children in microgravity or artificial gravity, potentially with elevated radiation levels, would be crucial to the success of the mission. Yet we have essentially no data on these processes beyond Earth. The social dynamics of small, isolated communities over extended periods present their own challenges. Historical examples of isolated human settlements, such as remote islands or frontier outposts, suggest that maintaining social cohesion, cultural continuity, and effective governance over generations can be problematic. For interstellar generation ships, these social factors could be as critical to mission success as the technical systems. Beyond these technical, biological, and social challenges lies a deeper philosophical question: why undertake such difficult journeys at all? The resources required for even a modest interstellar mission would be enormous. What benefits could justify such an investment? Scientific knowledge is one potential benefit. Close-up study of other stellar systems could provide invaluable insights into stellar and planetary formation, the potential for life beyond Earth, and the broader processes that shape our galaxy. Observations made from within another stellar system would offer perspectives impossible to achieve from Earth or even from space telescopes within our solar system. Resource acquisition is another potential motivation, though the practicality of returning resources across interstellar distances seems questionable with foreseeable technology. More plausible might be the establishment of human settlements around other stars, expanding the reach of humanity beyond our solar system, and providing a form of species-level insurance against catastrophic events in our home system. Perhaps the most compelling motivation is the fundamental human drive to explore, to push boundaries, to go where no one has gone before. Throughout history, humans have undertaken difficult and dangerous journeys of exploration, not for immediate practical benefit, but for the sake of discovery itself, and for the technological and cultural advances that often emerge from such endeavors. The challenges of interstellar travel are immense, spanning the domains of physics, engineering, biology, psychology, and sociology. Yet none of these challenges appear to be fundamentally insurmountable, given sufficient time, resources, and determination. They represent not walls but hurdles, obstacles to be overcome through sustained effort and innovation. As we consider these challenges, it is important to maintain a balance between realism about the difficulties and optimism about human ingenuity and perseverance. The history of space exploration has been one of overcoming seemingly impossible obstacles through creativity, determination, and collaborative effort. When President John F. Kennedy committed the United States to landing humans on the moon in the 1960s, the technological path to achieving that goal was far from clear. Yet within less than a decade, through focused effort and unprecedented investment, what had seemed like science fiction became reality. The challenges of interstellar travel are certainly greater, but so is the time frame within which we might address them. It is also worth noting that technological progress often occurs at an exponential rather than linear rate. The computing power available to the Apollo program that sent humans to the moon is dwarfed by that of modern smartphones. Materials undreamed of a century ago are now commonplace. Energy sources considered speculative a few decades ago are now commercially viable. If these trends continue, technologies that could enable interstellar travel might develop more rapidly than a linear projection would suggest. Moreover, we need not solve all the challenges of interstellar travel simultaneously. Incremental progress, addressing one obstacle at a time, can gradually build the foundation for eventual interstellar missions. Even if the first interstellar probes are small, simple, and slow compared to the grand visions of science fiction, they would represent a profound achievement and lay the groundwork for more ambitious missions to follow. The time dilation effects predicted by Einstein's theory of relativity add another fascinating dimension to interstellar travel. As a spacecraft approaches the speed of light, time aboard the craft passes more slowly than time on Earth, from the perspective of stationary observers. At speeds of 90% of the speed of light, this effect becomes significant, with 1 year passing on the spacecraft for about 2.3 years on Earth. This relativistic effect could, in principle, reduce the subjective travel time for human crews traveling at speeds very close to the speed of light. A journey of 40 light-years might take only a decade or so from the perspective of the travelers, though more than 40 years would still pass on Earth. This phenomenon offers a potential solution to the human lifespan limitation for extremely long journeys, though achieving the necessary speeds would require energy levels far beyond our current capabilities. However, time dilation also introduces its own social and psychological challenges. Crew members returning from a relativistic interstellar journey would find that much more time had passed on Earth than they had experienced. Family members and friends might have aged dramatically or died. Social and political structures might have changed unrecognizably, and the returning travelers would effectively be displaced in time as well as space. This temporal displacement could make returning to Earth after a relativistic interstellar journey a profoundly alienating experience. The travelers would be, in a very real sense, immigrants not just from another place, but from another time. The psychological impact of such displacement might be as challenging as the physical rigors of the journey itself. For one way, journeys or missions where crews establish permanent settlements around other stars, the time dilation effect would be less relevant. But conventional space travel, where being gone for 40 years of Earth time means you've experienced 40 years of travel time, is far more likely with technology we actually are able to build. We are more likely to have generation ships or suspended animation or digital copies of human minds than we are to have relativistic human interstellar travel. Still, it's a fascinating edge case to consider. The concept of relativity leads us to another profound challenge of interstellar travel: our place in time. The stars we observe in our night sky are not as they are now, but as they were when the light now reaching us left them, years or decades or centuries ago. When we send a probe to another star, we are sending it not to the star as we see it, but to the star as it will be when the probe arrives, potentially decades or centuries in the future. This temporal offset introduces uncertainty into mission planning. Conditions in the target star system may change between our last observations and the arrival of our probe. A potentially habitable planet might be rendered uninhabitable by a stellar flare or other astronomical event during the journey time. The world we send a probe to explore might be significantly different from the world the probe actually encounters upon arrival. For missions to nearby stars, this uncertainty is relatively modest, as stellar evolution typically occurs on timescales of millions or billions of years. However, for missions to more distant targets or for journeys taking many centuries, the potential for significant changes in the destination increases. This uncertainty adds another layer of complexity to the already formidable challenges of interstellar travel. The vast scale of interstellar distances also affects our perception of time in another way. The light travel time between stars means that any interstellar civilization would be spread across both space and time from the perspective of its members. A message sent from one stellar system to another would be received years or decades after it was sent, making real-time communication or coordination impossible across interstellar distances. This communication delay would fundamentally alter the nature of any interstellar human presence. Each stellar settlement would necessarily be largely autonomous, making its own decisions and developing its own cultural and technological trajectory, without the possibility of real-time guidance or intervention from Earth or other settlements. Over time, These separated communities might diverge significantly in language, culture, technology, and perhaps even biology, particularly if genetic engineering or other transformative technologies continue to advance. In effect, the light speed limit imposes not just a physical boundary, but a temporal one as well, creating what some futurists have called light cones of causality around each stellar system. Events within one system can only influence events in another system after a delay equal to the light travel time between them. This enforced delay could lead to a form of interstellar civilization, very different from the unified empires or federations often depicted in science fiction. The challenges of interstellar distance extend beyond the physical and technological to the philosophical and psychological. They force us to confront questions about the nature of human identity, community, and purpose that have no easy answers. What does it mean to be human when humanity is spread across multiple star systems with no possibility of real-time interaction? What kind of social structures and governance systems could function across such vast distances and times? How would individuals and communities maintain a sense of connection and shared purpose despite the enforced separation? These questions have no precedent in human experience. Throughout our history as a species, communication and travel times have steadily decreased, bringing human communities into ever closer contact. Interstellar settlement would reverse this trend, creating a future in which human communities are separated by boundaries more absolute than any in our past. Navigating this new reality would require not just technological innovation, but cultural and philosophical adaptation as well. Despite these challenges, the allure of the stars remains powerful. They represent not just scientific opportunities, but a kind of cosmic frontier, a vast unexplored territory waiting to be discovered. Throughout human history, frontiers have exerted a powerful pull on the human imagination, promising new knowledge, new resources, new ways of living, and new perspectives on our own society and culture. The American frontier of the 18th and 19th centuries, for example, not only expanded the physical territory of the United States, but profoundly shaped its national character, institutions, and self-conception. The frontier experience influenced American ideas about individualism, self-reliance, democracy, and the relationship between society and the natural world in ways that continue to resonate today. Similarly, an interstellar frontier might not just expand the physical reach of humanity, but transform our understanding of ourselves and our place in the cosmos. The experience of establishing human presence around other stars, of building new societies in environments utterly different from Earth, might lead to new forms of human culture, new philosophical and religious perspectives, and new approaches to age-old questions about the meaning and purpose of human existence. In this sense, the challenges of interstellar distance are not merely obstacles to be overcome, but opportunities for human growth and transformation. They invite us to transcend our current limitations, to develop new capabilities, and to reimagine what it means to be human in a cosmic context. They offer a kind of crucible for human evolution, not primarily biological but technological, cultural, and philosophical. The vastness of interstellar space also provides a context for reflecting on our own smallness and yet our remarkable significance. Earth, as Carl Sagan famously observed, is a pale blue dot when viewed from the outer reaches of our solar system, a tiny mote of dust in a sunbeam. Yet on this small world, life has flourished for billions of years, giving rise to beings capable of contemplating the cosmos, of sending robotic emissaries to other planets, and of dreaming about journeys to the stars. This paradox of human existence, our physical insignificance alongside our cognitive and cultural richness, becomes even more striking when considered against the backdrop of interstellar distances. We are but one species on one small planet orbiting one ordinary star among hundreds of billions in our galaxy alone. Yet we possess the capacity to comprehend the vastness that surrounds us, to build tools that extend our senses across space and time, and to envision futures in which our descendants might spread beyond our home world to explore and perhaps inhabit worlds orbiting other suns. The challenges of interstellar distance, then, are not just technical problems to be solved, but invitations to reimagine our place in the cosmos and our potential as a species. They remind us of the vastness that surrounds us and the limitations that constrain us, while simultaneously encouraging us to dream beyond those limitations, to envision futures in which humanity's reach extends beyond the confines of our solar system to touch the stars. As we grapple with these challenges, we are engaged in a process of becoming not just a spacefaring species, but a truly cosmic one, a form of life that has transcended its planetary origins to embrace the broader universe. This transition, from an Earth-bound to a cosmic perspective, may be as significant in the long arc of human history as the transition from hunter-gatherer societies to agricultural ones, or from pre-industrial to technological civilization. The poet T.S. Eliot wrote, "We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time." In the context of interstellar travel, these words take on a new resonance. Our journeys to other stars, whether undertaken physically by spacecraft or virtually through telescopic observations and computer models, may ultimately lead us back to a renewed appreciation of our home planet, seen now, not in isolation, but as part of a vast cosmic tapestry. Perhaps this is the deepest significance of confronting the challenges of interstellar distance, not that we will necessarily overcome them completely, but that in the attempt, we will develop new ways of seeing ourselves and our world, new technologies that improve life on Earth, and new cultural and philosophical perspectives that enrich human existence, regardless of whether we ever succeed in sending humans to other stars. As we conclude our exploration of the challenges of interstellar distance, let us acknowledge their magnitude while maintaining hope in human ingenuity and determination. The stars are far, but not unreachable. The journey will be long and difficult, but not impossible. The obstacles are formidable, but not insurmountable. With patience, creativity, and collaborative effort, humanity may yet find ways to bridge the vast gulfs between stars, extending our presence and our understanding into the cosmic ocean that surrounds us. The stars have shone down upon Earth since before humans existed to gaze up at them. They have inspired wonder, sparked curiosity, guided navigation, and fueled scientific inquiry throughout human history. Now they beckon us toward a new chapter in our story, one in which we transcend the boundaries of our home planet to become a truly interstellar species. The challenges are great, but so is the promise. The journey continues, one step at a time, toward the stars. At the heart of humanity's quest to reach the stars lies what engineers and physicists call the propulsion problem. How do we move a spacecraft across the vast gulfs of interstellar space within a time frame meaningful to human civilization? This is not merely a technical challenge, but a fundamental confrontation with the laws of physics as we currently understand them. In this chapter, we will explore the various propulsion concepts that might one day carry us to other stars, from extensions of familiar technologies to speculative ideas that brush against the boundaries of known science. Traditional rocket propulsion, which has carried humans to the moon and robotic explorers throughout our solar system, relies on Newton's third law of motion. For every action, there is an equal and opposite reaction. A rocket expels mass in one direction, generally through the combustion of fuel, and the spacecraft moves in the opposite direction. This principle is captured in the Tsiolkovsky rocket equation, which relates the change in velocity of a rocket to the exhaust velocity of its propellant and the ratio of initial mass, including fuel, to final mass. Chemical rockets, which have been the workhorses of space exploration since its inception, use the energy released by chemical reactions between fuel and oxidizer to accelerate exhaust gases to high velocities. The Space Shuttle's main engines, for example, burned hydrogen and oxygen to produce superheated water vapor, which was expelled from the nozzle at velocities of about 4.5 kilometers per second. While chemical rockets have served us well for missions within our solar system, they face fundamental limitations for interstellar travel. The energy density of chemical bonds is relatively low, limiting the exhaust velocities that can be achieved. Even the most energetic chemical reactions produce exhaust velocities of only a few kilometers per second, far below what would be needed for practical interstellar journeys. Moreover, the exponential nature of the rocket equation means that as the desired change in velocity increases, the ratio of initial mass to final mass grows at an accelerating rate. For the velocities needed for interstellar travel, perhaps 10 to 20% of the speed of light, a chemical rocket would need to be almost all fuel, with virtually no mass left for the payload or spacecraft structure. To illustrate this limitation, consider a mission to Alpha Centauri with a cruise velocity of just 1% of the speed of light, about 3,000 kilometers per second. Using chemical propulsion with an exhaust velocity of 4.5 kilometers per second, the initial mass of the spacecraft would need to be about 3 times 10 to the 285th power times its final mass. This number is so astronomically large that it exceeds the estimated number of atoms in the observable universe. Clearly, chemical propulsion alone cannot solve the interstellar propulsion problem. Nuclear fission, the process that powers current nuclear power plants and some naval vessels, offers significantly higher energy density than chemical reactions. In a fission reaction, heavy atomic nuclei such as uranium or plutonium split into lighter elements, releasing energy in the process. The energy released per unit mass is approximately 1 million times greater than in chemical reactions. Several concepts for nuclear fission propulsion have been proposed and studied. The most straightforward approach is nuclear thermal propulsion, in which a nuclear reactor heats a propellant, typically hydrogen, which is then expelled through a nozzle to generate thrust. This approach can achieve exhaust velocities of 8 to 12 kilometers per second, about twice that of the best chemical rockets. Project Orion, conceived in the 1950s and 60s, proposed a more direct use of nuclear energy for propulsion. The Orion concept involved detonating a series of small nuclear bombs behind a massive pusher plate attached to the spacecraft by shock absorbers. Each detonation would impart momentum to the plate, accelerating the spacecraft. Theoretical studies suggested that such a system could achieve exhaust velocities of around 20 to 30 kilometers per second. While Project Orion could potentially achieve higher velocities than nuclear thermal propulsion, it faced significant practical and political obstacles, including concerns about nuclear fallout from launches within Earth's atmosphere and the international treaties banning nuclear explosions in space. Nevertheless, it represented an early attempt to grapple with the enormous energy requirements of interstellar travel. Nuclear pulse propulsion was revisited in the 1970s with Project Daedalus, a theoretical study by the British Interplanetary Society. Daedalus proposed using fusion rather than fission reactions in the form of small pellets of deuterium and helium-3 that would be detonated by electron beams behind the spacecraft. This approach promised higher exhaust velocities, potentially up to 30,000 kilometers per second, or 10% of the speed of light. Project Daedalus envisioned a 2-stage spacecraft with a total initial mass of 54,000 metric tons, most of which would be fuel. It would accelerate for about 4 years to reach a cruise velocity of 12% of the speed of light, allowing it to reach Barnard's star, about 6 light-years away, in about 50 years. However, the design did not include any means of deceleration, so the spacecraft would simply fly through the target star system, making observations during its brief passage. Nuclear fusion, the process that powers the Sun and other stars, offers even higher energy density than fission. In fusion reactions, light atomic nuclei combine to form heavier nuclei, releasing energy in the process. The most accessible fusion reaction involves deuterium and tritium, isotopes of hydrogen, which fuse to form helium and release a high-energy neutron. Fusion propulsion concepts generally involve creating and containing a plasma of fusion fuel at temperatures of millions of degrees, confining it with magnetic fields to prevent it from touching and melting the spacecraft structure, and directing the energetic particles produced by the fusion reactions to generate thrust. Theoretical studies suggest that fusion rockets could achieve exhaust velocities of up to 20% of the speed of light, making interstellar travel within a human lifetime potentially feasible. However, achieving controlled fusion for power generation on Earth has proven to be a formidable challenge, with decades of research yet to produce a fusion reactor that generates more energy than it consumes. The additional challenges of miniaturizing such a reactor for spacecraft propulsion and designing systems to efficiently convert fusion energy into thrust make fusion propulsion a technology that, while promising, remains decades or centuries from practical implementation. Antimatter, the mirror image of normal matter with opposite charge and quantum properties, offers the highest theoretical energy density of any known fuel. When matter and antimatter come into contact, they annihilate each other, converting all of their mass into energy according to Einstein's famous equation, E=mc². This complete conversion of mass to energy makes antimatter about 1,000 times more energy dense than fusion and 100 million times more energy dense than chemical reactions. An antimatter rocket would bring together matter and antimatter in a controlled manner, directing the resulting energy to generate thrust. Theoretical studies suggest that such a propulsion system could achieve exhaust velocities approaching the speed of light, potentially enabling interstellar journeys with acceleration and deceleration phases that keep the total trip time within a human lifetime. However, antimatter propulsion faces even more formidable practical obstacles than fusion. Current technology can produce only minute quantities of antimatter, measured in nanograms, at enormous cost. The entire world's annual production of antimatter would power a light bulb for only a few minutes. Moreover, storing antimatter is extraordinarily challenging, as it annihilates upon contact with normal matter, requiring complex electromagnetic containment systems. While these fundamental physical and technological limitations make antimatter propulsion appear impractical with current technology, it remains a tantalizing possibility for the distant future. If methods of producing, storing, and utilizing antimatter more efficiently could be developed, it could provide a path to the stars that obeys all known laws of physics while enabling journey times of decades rather than millennia. The propulsion concepts discussed thus far all rely on carrying fuel on board the spacecraft, whether chemical, nuclear, or antimatter. An alternative approach is to separate the propulsion system from the payload, using external energy sources to accelerate a relatively small spacecraft to high velocities. This concept underlies various beamed propulsion approaches. Solar sails, which use the pressure of sunlight to propel a spacecraft, represent a first step in this direction. Light, whether from the sun or artificial sources, carries momentum and exerts pressure when it reflects off a surface. A large, lightweight reflective sail can capture this pressure to gradually accelerate a spacecraft without carrying any onboard propellant. Solar sails work best in the inner solar system, where the sun's light is most intense. As a spacecraft moves farther from the sun, the available light pressure decreases with the square of the distance, limiting the usefulness of solar sails for interstellar missions based on sunlight alone. However, the basic principle of light pressure can be extended using artificial light sources, typically powerful lasers, to create what are known as laser sails or light sails. The Breakthrough Starshot initiative, announced in 2016, proposes using a ground-based array of lasers to accelerate a fleet of tiny spacecraft, each weighing only a few grams and carrying miniaturized scientific instruments to about 20% of the speed of light. These nanocraft would be attached to lightweight sails a few meters across, made of materials only a few hundred atoms thick. The laser array would focus a beam with a power of about 100 gigawatts on each sail for a few minutes, accelerating the nanocraft to its cruise velocity within the inner solar system. At 20% of the speed of light, these nanocraft could reach Alpha Centauri in about 20 years, plus the 4.37 years it would take for their signals to return to Earth. This represents the most near-term concept for interstellar exploration within a human lifetime, though it still requires significant advances in laser technology, materials, science, and miniaturization of scientific instruments. However, the Breakthrough Starshot concept includes no provision for deceleration at the target star system. The nanocraft would zip through Alpha Centauri in a matter of hours, having just enough time to take some images and make basic measurements before the opportunity is lost. Moreover, the tiny size of the spacecraft would severely limit the scientific payload and the power available for transmitting data back to Earth. Despite these limitations, the laser sail approach represents a potentially viable path to our first interstellar missions. By drastically reducing the mass of the spacecraft and leaving the bulky power source behind, it sidesteps many of the challenges faced by traditional propulsion concepts. Another variant of beamed propulsion is the microwave sail, which uses high-powered microwave beams rather than lasers to accelerate a spacecraft. Microwaves have the advantage of being easier and potentially less expensive to generate in large quantities than laser light, though they cannot be focused as tightly over long distances, potentially limiting the range over which effective acceleration can be maintained. Both laser and microwave sails face the challenge of maintaining precise aim of the beam over interstellar distances. Even tiny deviations could cause the beam to miss the sail, cutting off the propulsion. Moreover, the sail itself must be extraordinarily lightweight, yet strong enough to withstand the intense power of the beam without tearing or melting. Beyond these beamed propulsion concepts lie more speculative ideas that, while consistent with known physics, push the boundaries of current engineering capabilities. One such concept is the Bussard ramjet, proposed by physicist Robert Bussard in 1960. The Bussard ramjet would use enormous magnetic fields to collect hydrogen from the interstellar medium, funnel it into a fusion reactor, and use the energy produced to accelerate the spacecraft. In principle, this would solve the fuel problem, as the spacecraft would gather its propellant from space itself, rather than carrying it along from the start. However, the interstellar medium is extraordinarily tenuous, with an average density of about 1 hydrogen atom per cubic centimeter. To gather significant amounts of fuel, the magnetic scoop would need to have a cross-sectional area of many kilometers, presenting enormous engineering challenges. Moreover, calculations suggest that the drag created by scooping up the interstellar medium might exceed the thrust generated, particularly at the relativistic speeds that would make interstellar travel practical. Another speculative concept is the nuclear saltwater rocket, proposed by Robert Zubrin in the late 20th century. This design would use a solution of uranium salts in water as a propellant. As the solution flows out of the rocket, it would reach critical mass, initiating a continuous nuclear reaction in the exhaust stream itself, rather than in a contained reactor. Theoretical calculations suggest such a system could achieve exhaust velocities approaching 1% of the speed of light. While the nuclear saltwater rocket remains within the bounds of known physics, the practical challenges of containing and controlling such an energetic and radioactive propulsion system are formidable. Moreover, like all nuclear propulsion concepts, it would face significant regulatory and safety hurdles. Moving even further into the realm of speculative physics, we encounter concepts that rely on manipulating space-time itself, rather than accelerating a spacecraft through space in the conventional sense. The most famous of these is the Alcubierre warp drive, proposed by theoretical physicist Miguel Alcubierre in 1994. The Alcubierre drive would create a bubble of normal space around a spacecraft, contracting space in front of the bubble and expanding it behind, effectively moving the bubble and the spacecraft within it through space faster than light. Unlike conventional propulsion, this approach does not involve the spacecraft itself exceeding the speed of light relative to its local space, avoiding the prohibition on faster-than-light travel established by Einstein's theory of relativity. However, the Alcubierre drive requires negative energy density to function, something that has never been observed in large quantities in nature and may be fundamentally impossible to create in the amounts needed. Moreover, calculations suggest that even if such a drive could be built, it would require as much energy as the mass of Jupiter converted completely to energy to operate, far beyond our current or foreseeable energy production capabilities. Other theoretical, faster-than-light propulsion concepts include traversable wormholes, hypothetical tunnels through space-time that could connect distant points in the universe. Like the Alcubierre drive, traversable wormholes would require negative energy density to hold open against their natural tendency to collapse. They also raise complex questions about causality and the potential for time travel, as a network of wormholes could in principle allow travel into the past, creating paradoxes that the laws of physics seem designed to prevent. While these speculative faster-than-light concepts are intriguing and continue to be studied by theoretical physicists, they remain firmly in the realm of science fiction rather than near-term engineering possibilities. Any serious planning for interstellar missions in the coming centuries must rely on propulsion systems that operate within the well-established laws of physics, which currently indicate that faster-than-light travel is impossible. Returning to more near-term possibilities, ion drives represent an existing technology that, while not capable of interstellar velocities in their current form, illustrate principles that might contribute to future interstellar propulsion systems. Ion drives use electrical power, typically from solar panels, to ionize a propellant such as xenon and accelerate the resulting ions using electromagnetic fields. Current ion drives produce very low thrust but can operate for months or years, gradually building up significant velocity changes. The Dawn spacecraft, which orbited both the asteroid Vesta and the dwarf planet Ceres, used ion propulsion to achieve a velocity change of more than 10 kilometers per second over the course of its mission, a record for a spacecraft propulsion system. The high exhaust velocity of ion drives, typically 30 to 50 kilometers per second, makes them much more fuel efficient than chemical rockets. However, their very low thrust and dependence on external power sources make them impractical for rapid interstellar travel. A more powerful variant, the Variable Specific Impulse Magnetoplasma Rocket, or VASIMA, could potentially achieve higher thrust while maintaining high exhaust velocity, but would still fall far short of the performance needed for interstellar missions. Another existing technology with potential applications for interstellar precursor missions is radioisotope power, which uses the heat generated by the decay of radioactive materials to generate electricity. The Voyager probes, now in interstellar space, are powered by radioisotope thermoelectric generators using plutonium-238, which has a half-life of 88 years. While radioisotope power does not directly provide propulsion, it enables spacecraft to operate far from the Sun, where solar power becomes impractical. Future interstellar missions might use advanced radioisotope power combined with ion propulsion or other electric propulsion technologies for extended operations in the outer solar system and beyond. Gravitational assists, another technique used in existing missions, use the gravity of planets to change a spacecraft's trajectory and speed without expending fuel. The Voyager probes used gravity assists from Jupiter and Saturn to gain enough energy to escape the solar system. While gravitational assists alone cannot accelerate a spacecraft to interstellar velocities, they might play a role in the early phases of an interstellar mission, providing an initial boost before other propulsion systems take over. As we survey the landscape of propulsion technologies, from the proven but limited capabilities of chemical rockets to the speculative possibilities of space-warping drives, we see a spectrum of options with varying degrees of technical feasibility and performance potential. The near-term prospects for interstellar travel appear to lie with lightweight probes accelerated by beamed propulsion, while more substantial missions carrying humans or large scientific payloads would require significant advances in nuclear or antimatter propulsion over timeframes of many decades or centuries. The propulsion problem, central to the challenge of interstellar travel, illustrates a broader truth about our quest to reach the stars. It is a multi-generational endeavor, requiring sustained effort and incremental progress across multiple fields of science and engineering. The first interstellar missions will likely be modest in scale and scientific return, laying the groundwork for more ambitious efforts as our technological capabilities advance. This incremental approach has precedent in the history of terrestrial exploration. The first European voyages to the Americas were limited in scope and often one-way journeys, with many ships lost along the way. Over time, naval technology improved, routes became better understood, and what was once an extraordinary undertaking became commonplace. The exploration of space, including interstellar space, may follow a similar trajectory, with early high-risk missions gradually giving way to more routine operations as technology matures. The various propulsion concepts we have explored also illustrate the interplay between theoretical physics and practical engineering in the quest for interstellar travel. Some approaches, like fusion and antimatter propulsion, are well grounded in established physics, but face enormous engineering challenges. Others, like the Alcubierre drive, are more speculative from a physics perspective, but have been the subject of serious theoretical work. Still others, like solar and laser sails, involve well-understood physics and are closer to current engineering capabilities, but offer more limited performance. This diversity of possibilities suggests that the path to the stars may not be singular but multifaceted, with different propulsion technologies finding different applications based on mission requirements and the state of technological development. Small, fast probes might use laser sail propulsion, while larger scientific platforms might rely on nuclear electric or fusion systems operating over longer timeframes. One framework for thinking about this progression is the notion of interstellar precursor missions, which would venture beyond our solar system but fall short of reaching other stars. Such missions could explore the local interstellar medium, study the heliosphere from the outside, and test technologies that might later be applied to true interstellar missions. These stepping stone projects would build experience and confidence while delivering valuable scientific returns in their own right. The propulsion problem also highlights the interconnectedness of different technological domains. Advances in materials science, for example, could enable stronger, lighter sails for beamed propulsion or more durable containment vessels for fusion reactions. Progress in artificial intelligence might allow for more autonomous spacecraft operation, essential for missions spanning decades or centuries. Breakthroughs in power generation and storage could enable more powerful ion drives or laser arrays. This interconnectedness suggests that progress toward interstellar travel will not be isolated, but will both draw from and contribute to broader technological advancement. Technologies developed to address the unique challenges of interstellar propulsion may find applications in other domains, from energy production to transportation to manufacturing, creating a virtuous cycle of innovation. The enormity of the propulsion challenge has led some to question whether interstellar travel is a realistic goal for humanity, whether the resources required might be better directed toward other needs. While these concerns are valid, they perhaps overlook the inspirational and aspirational value of reaching for the stars, even if the journey takes centuries to complete. Throughout history, grand challenges have spurred human creativity and collaboration in ways that transcend their specific objectives. The Apollo program, aimed at landing humans on the moon, accelerated developments in computing, materials science, telecommunications, and other fields with applications far beyond space exploration. Similarly, the challenge of interstellar travel, even if not fully realized for generations, may catalyze innovations with widespread benefits. Moreover, the long-term survival and flourishing of humanity may ultimately depend on our ability to extend our presence beyond the solar system. While the timeframe for such existential concerns may be measured in millennia rather than centuries, developing the capability for interstellar travel represents a form of cosmic insurance policy, a hedge against the possibility of catastrophic events in our home system. The propulsion problem, then, is not merely a technical puzzle to be solved, but a gateway to a broader engagement with our cosmic environment and our long-term future as a species. It invites us to expand our horizons, both literally in terms of the distances we can traverse, and figuratively, in terms of the timeframes we consider and the possibilities we envision. As we conclude our exploration of the propulsion problem, let us acknowledge its formidable nature while maintaining hope in human ingenuity and perseverance. The stars are distant, but not unreachable. The journey will be long and challenging, but not impossible. With sustained effort and incremental progress, humanity may yet develop the means to reach beyond our solar system to explore the cosmic neighborhood that surrounds us. The propulsion technologies that will ultimately carry us to the stars may not yet exist in functional form, and the scientists and engineers who will perfect them may not yet have been born. Yet each step we take toward understanding the challenges and possibilities brings us closer to a future in which the gaps between stars are not barriers but pathways, not voids but bridges to new worlds and new discoveries. The stars have shone down upon Earth for billions of years, bearing silent witness to the emergence and evolution of life, the rise of human civilization, and our first tentative steps into space. With patience, creativity, and determination, we may yet find ways to return their gaze up close, to explore the worlds that orbit them, and perhaps to establish human presence among them. The journey continues, one innovation at a time, toward the stars. Among the various approaches to interstellar travel we have explored, perhaps none is as tantalizing in its near-term potential as the concept of light sail propulsion. In particular, the Breakthrough Starshot initiative represents the most well-developed and well-funded effort to date aimed at sending spacecraft to another star within a human lifetime. In this chapter, we will delve into the details of Project Starshot and the broader category of light sail missions, examining their potential, their challenges, and what they might mean for humanity's first steps beyond our solar system. The fundamental principle behind light sail propulsion is both elegant and well established in physics. Light, though it has no mass, carries momentum. When light reflects off a surface, it imparts a small but measurable force, a phenomenon known as radiation pressure. This effect was predicted by James Clerk Maxwell in the 19th century and experimentally confirmed in the early 20th century. While the pressure exerted by light is exceedingly small, about 9 micronewtons per square meter at Earth's distance from the Sun, it can produce significant acceleration when applied to a very lightweight, reflective sail in the vacuum of space. Unlike conventional rockets, which must carry their propellant with them, a light sail craft uses an external energy source, whether the Sun or a directed beam from Earth, to provide its propulsion. The concept of solar sails, which use the Sun's light for propulsion, has been studied for decades and demonstrated in missions like Japan's Ikaros, launched in 2010, and the Planetary Society's LightSail 2, launched in 2019. These missions confirmed the viability of light sail technology for propulsion within our solar system. However, for interstellar missions, solar sails face a fundamental limitation. The intensity of sunlight decreases with the square of the distance from the Sun. By the time a spacecraft reaches the outer edge of our solar system, the available solar pressure is too weak to provide meaningful acceleration. This is where the concept of beamed propulsion enters the picture. Rather than relying on the diffuse light of the Sun, beamed propulsion uses a powerful, directed energy source, typically a laser or microwave beam, to illuminate the sail. This approach offers several advantages. The beam can be focused to maintain its intensity over longer distances. The power of the beam can be much greater than the solar radiation available at Earth's orbit, and the beam can be directed precisely at the sail to maximize the efficiency of the propulsion. The Breakthrough Starshot initiative, announced in 2016, aims to use this beamed propulsion approach to send a fleet of tiny spacecraft to Alpha Centauri within a human lifetime. The project is part of the Breakthrough Initiatives, a suite of scientific programs founded by Russian-Israeli entrepreneur Yuri Milner and supported by other prominent figures, including the late Stephen Hawking and Mark Zuckerberg. The concept behind Starshot is both ambitious and elegant in its simplicity. The plan calls for the development of gram-scale spacecraft, dubbed Starships, each no larger than a postage stamp, but containing a full suite of miniaturized scientific instruments, power systems, and communication capabilities. These starships would be attached to lightweight sails a few meters across, made of materials just a few hundred atoms thick. A ground-based array of lasers, with a combined power output of about 100 gigawatts, would focus its beam on the sails, accelerating them to approximately 20% of the speed of light within a matter of minutes. At this velocity, the spacecraft could reach Alpha Centauri in about 20 years, plus the 4+ years it would take for the data they collect to be transmitted back to Earth. The scale of the Starshot concept is simultaneously modest and monumental. The spacecraft themselves would be tiny, with minimal capabilities compared to the sophisticated probes we have sent throughout our solar system. Yet the infrastructure required to launch them, particularly the massive laser array, would represent one of the most ambitious engineering projects ever undertaken, comparable in scale and complexity to the largest scientific instruments currently in existence, such as the Large Hadron Collider or the Square Kilometre Array. The choice of Alpha Centauri as the destination for Starshot is no coincidence. As our nearest stellar neighbor, it offers the shortest travel time for a given spacecraft velocity. Moreover, the discovery of the potentially habitable planet Proxima Centauri b in 2016, the same year Starshot was announced, provided an enticing scientific target for the mission. The prospect of capturing even rudimentary images and measurements of an Earth-sized planet orbiting another star represents a scientific opportunity of unparalleled significance. The technical challenges facing Starshot are formidable, but, crucially, appear to be engineering problems rather than requiring new physics. Each aspect of the mission pushes the boundaries of current technology, but builds upon established principles and ongoing research in materials science, laser physics, electronics miniaturization, and other fields. The sail material, for instance, must be extraordinarily lightweight, yet strong enough to withstand the intense laser beam without tearing or melting. Current research focuses on metamaterials just a few atoms thick, potentially made from substances like graphene, with carefully designed optical properties to maximize reflectivity while minimizing absorption of the laser energy. These materials must also be able to withstand the harsh conditions of interstellar space over a journey of decades, including impacts with interstellar dust and gas, radiation damage, and extreme temperature variations. Creating and testing such materials represents a significant materials science challenge, but one that builds upon ongoing research in nanotechnology and advanced materials. The Starship itself, the tiny spacecraft that would carry the scientific instruments, power systems, and communication equipment, represents a different kind of engineering challenge. It must pack all the capabilities of a traditional space probe into a package weighing just a few grams and consuming minimal power. This miniaturization builds upon trends in consumer electronics, where devices like smartphones already pack sophisticated sensors, processors, and communication systems into small, energy-efficient packages. For Starshot, the miniaturization would need to go much further, creating what are essentially fully functional spacecraft on a chip. The instruments would likely include cameras for imaging Alpha Centauri and its planets, magnetometers for measuring magnetic fields, particle detectors for studying the interstellar medium, and potentially spectroscopic capabilities for analyzing the composition of planetary atmospheres. Powering these instruments over a journey of decades represents another challenge. Traditional solar panels would be ineffective in the darkness of interstellar space, far from any star. Radioisotope power, used in missions like the Voyager probes, would be too heavy for the gram-scale starships. Instead, Starshot might rely on advanced battery technologies, potentially supplemented by the collection of power from the laser beam during the acceleration phase, and extreme power efficiency during the cruise phase, with systems hibernating for most of the journey and waking periodically to make observations and send status updates. Communication across interstellar distances with such a tiny spacecraft poses perhaps the most daunting challenge. The starships would need to transmit data over a distance of more than 4 light-years, with a power budget of just a few watts at most. This would require extraordinarily sensitive receivers on Earth, and likely some form of optical communication, rather than traditional radio. One proposal involves using the Starship's sail as a reflector to bounce a laser beam back to Earth, modulating the reflection to encode data. This would effectively use Earth-based infrastructure to provide most of the power needed for communication, with the Starship itself serving primarily as a reflector and modulator rather than a powerful transmitter. Even with such innovative approaches, the data return from Starshot would be limited compared to what we've come to expect from missions within our solar system. The images returned might be low resolution, and the total data volume might be measured in megabytes, rather than the gigabytes or terabytes returned by missions like the Mars rovers or the New Horizons Pluto flyby. However, even such limited data would represent our first close-up observations of another stellar system, a scientific milestone of incalculable value. The laser array needed to accelerate the starships to 20% of the speed of light represents perhaps the most visible and costly component of the Starshot infrastructure. With a proposed power output of about 100 gigawatts, it would be comparable to the output of a large nuclear power plant, or about 1% of the total electricity consumption of the United States. This massive array would likely consist of millions of individual lasers, precisely coordinated to focus their beams on the sails of the starships. The technology for such high-power lasers exists today, though not at the scale required for Starshot. The coordination of millions of individual beams to maintain focus on a small, potentially moving target over distances of millions of kilometers represents a significant engineering challenge. The laser array would need to be located in an area with stable, clear atmospheric conditions to minimize distortion of the beam, possibly in a high-altitude desert location. It would also need to be built away from major population centers and air traffic corridors, as the powerful laser could pose hazards to aircraft and potentially to satellites if not carefully managed. One intriguing aspect of the Starshot infrastructure is that, once built, it could be used to launch multiple missions to different stellar destinations. The laser array and associated systems for tracking and communicating with the starships would represent most of the cost of the project. The starships themselves would be relatively inexpensive to produce in large numbers, allowing for redundancy in the mission design and potentially enabling simultaneous or sequential missions to multiple targets. This scalability is one of the compelling aspects of the Starshot concept. Traditional spacecraft are one-off designs, each representing a major investment of resources and engineering effort. The Starshot architecture, once established, could support an ongoing program of interstellar exploration, with improvements and refinements incorporated into successive generations of starships. Despite these advantages, the Starshot concept faces significant limitations and challenges. Perhaps the most fundamental is that the starships would fly through the Alpha Centauri system at 20% of the speed of light, giving them only hours to make observations and transmit data before they pass beyond the system, never to return. There is no provision in the current design for slowing down upon arrival, as this would require a second propulsion system comparable in power to the laser array, either carried along with the Starship or somehow pre-positioned in the Alpha Centauri system. This flyby approach drastically limits the scientific return compared to orbital missions, which can study their targets for years or even decades. A Starshot mission would capture only a brief snapshot of the Alpha Centauri system, albeit one of unparalleled scientific significance as our first close-up view of another stellar system. Another limitation is the vulnerability of such tiny spacecraft to damage during their decades-long journeys. Even a micrometeoroid impact that would be insignificant to a conventional spacecraft could be catastrophic to a gram-scale starship. The interstellar medium, while extraordinarily tenuous by earthly standards, still contains dust particles that could impact the spacecraft at relative velocities of thousands of kilometers per second, potentially damaging or destroying critical systems. Radiation damage over decades of exposure to cosmic rays and other high-energy particles could also degrade the electronic systems of the starships, potentially rendering them inoperable before they reach their destination. Shielding against such radiation would add mass, conflicting with the need for the spacecraft to be as lightweight as possible for effective light sail propulsion. These vulnerabilities point to the need for redundancy in the mission design. Rather than sending a single starship, Starshot envisions launching hundreds or thousands, accepting that many will fail, but counting on some fraction to survive the journey and successfully return data. This swarm approach increases the chances of mission success, but also adds complexity to the tracking and communication systems needed to maintain contact with multiple spacecraft over interstellar distances. The Breakthrough Starshot Initiative has assembled a team of scientists and engineers to study these challenges and develop potential solutions. The project is currently in a research and development phase, with funding from breakthrough initiatives supporting work on various aspects of the mission concept, from sail materials to communication systems to laser array designs. The timeline for Starshot is measured in decades rather than years. The initial announcement in 2016 indicated a target of about 20 years for technology development, followed by the construction of the laser array and other infrastructure, the launch of the starships, and then the 20-plus-year journey to Alpha Centauri. This would put the return of data from Alpha Centauri in the second half of the 21st century at the earliest, assuming no major delays or technical setbacks. This extended timeline highlights an important aspect of interstellar missions. They are inherently multi-generational endeavors. Many of the scientists and engineers who initiate such projects will not live to see their completion. This requires a different approach to project planning and institutional continuity than is typical for space missions within our solar system, which generally return data within years, or at most a decade or two after launch. Despite these challenges, the Breakthrough Starshot Initiative represents the most concrete and well-funded effort to date aimed at achieving interstellar flight within the 21st century. Its focus on light sail technology, leveraging the concept of beamed propulsion, offers a path forward that does not require fundamental breakthroughs in physics or propulsion theory, though it does push the boundaries of engineering in multiple domains. Beyond Starshot, other light sail concepts are being studied for interstellar and near-interstellar missions. The breakthrough initiatives are also supporting research on a precursor mission called Starlight, which would demonstrate the key technologies of Starshot at a smaller scale, potentially sending a probe to the outer solar system or even into nearby interstellar space, though not all the way to another star. NASA has studied concepts like the Interstellar Probe, which would use conventional propulsion augmented by a gravity assist from the Sun to send a more traditional spacecraft into nearby interstellar space, potentially reaching distances of 1,000 astronomical units or more from the Sun. While not a true interstellar mission in the sense of reaching another star, such a probe would venture far beyond the heliosphere, the bubble of solar influence that defines the boundary of our solar system, providing valuable data about the interstellar medium and serving as a stepping stone toward more ambitious missions. The European Space Agency has similarly studied concepts for interstellar precursor missions, including the Interstellar Heliopause probe and the more ambitious KISS, or Kilo Satellite Swarm, for interstellar sky scanning, which would use a swarm of small satellites similar in concept to the starships, though targeted at exploring the outer reaches of our solar system rather than reaching other stars. These various initiatives highlight the growing interest in pushing the boundaries of space exploration beyond the traditional confines of our solar system. While true interstellar missions to other stars remain at the frontier of what is technologically feasible, interstellar precursor missions that venture beyond the heliosphere but fall short of reaching other stars appear to be within reach of current or near-future technology. The appeal of light sail propulsion for these missions lies in its fundamental efficiency. By leaving the energy source behind and carrying only the lightweight sail and payload, such systems can potentially achieve much higher final velocities than traditional rocket propulsion, where the need to carry fuel imposes severe constraints due to the exponential relationship between the desired velocity change and the required fuel mass. However, light sail propulsion is not without its limitations and challenges. The acceleration provided by light pressure, even from a powerful laser, is extremely gentle, requiring a very lightweight spacecraft to achieve meaningful velocities. This limits the payload mass, and thus the scientific capabilities of the spacecraft. The sail itself must be extraordinarily thin yet strong, highly reflective, and able to withstand both the intense energy of the laser beam during acceleration and the harsh conditions of interstellar space during the cruise phase. Current materials like aluminized mylar, used in solar sail demonstrations within our solar system, are too heavy for effective acceleration to interstellar velocities. New materials like graphene or other two-dimensional structures may offer the combination of lightweight, strength, and reflectivity needed, but their production and integration into functioning sails represents a significant engineering challenge. The stability and control of a light sail during the acceleration phase poses another challenge. A perfectly symmetric sail illuminated by a perfectly centered beam would accelerate in a straight line. However, any asymmetry in the sail or misalignment of the beam would induce rotation or off-axis acceleration, potentially sending the spacecraft off course. Some form of active control would likely be needed to maintain the desired trajectory during acceleration, adding complexity to the already challenging design of a gram-scale spacecraft. For human-scale payloads, the challenges of light sail propulsion become even more acute. The sail area required scales with the mass of the payload, meaning that a human mission with a mass of hundreds or thousands of tons would require a sail of enormous dimensions, potentially kilometers across. The laser power needed to accelerate such a massive spacecraft to interstellar velocities would be correspondingly greater, potentially requiring power levels beyond what could reasonably be generated and directed from Earth. This limitation highlights a general principle in interstellar mission design. There is often a trade-off between payload mass, cruise velocity, and technological complexity. Lighter payloads can potentially achieve higher velocities with a given propulsion system, but may have limited capabilities once they reach their destination. Heavier payloads offer more capability, but require more powerful propulsion systems to achieve meaningful interstellar velocities. The Breakthrough Starshot concept represents one point in this design space, prioritizing cruise velocity to achieve a journey time of decades rather than millennia, at the cost of a very limited payload mass and thus limited scientific capabilities. Other interstellar mission concepts make different trade-offs, such as accepting lower cruise velocities and longer journey times in exchange for more substantial payloads and greater scientific return. Despite these challenges and limitations, light sail missions offer perhaps the most promising near-term approach to interstellar exploration. By leveraging external energy sources rather than carrying fuel, they sidestep one of the fundamental limitations of traditional rocket propulsion. By focusing on miniaturized payloads, they align with broader trends in spacecraft design towards smaller, more capable systems enabled by advances in electronics, materials, science, and miniaturization. The potential scientific return from even a modest interstellar mission would be enormous. Direct measurements of the interstellar medium, uncontaminated by the influence of our Sun, would provide valuable data for astrophysicists. Close-up observations of another stellar system would reveal details impossible to discern from Earth, potentially including the atmospheric composition of exoplanets, the structure of circumstellar dust and gas, and the interactions between the star's stellar wind and the surrounding interstellar medium. Beyond these scientific returns, an interstellar mission would represent a profound milestone in human exploration, our first direct physical contact with another stellar system. Just as the Apollo landings on the Moon and the Voyager encounters with the outer planets expanded our perspective and captured the imagination of people around the world, an interstellar mission would mark a new chapter in humanity's engagement with the cosmos. The very act of undertaking such a mission, of extending our reach beyond the confines of our solar system, would be a statement about human capabilities and aspirations. It would demonstrate our ability to conceive and execute projects on multi-generational timescales, to develop technologies that push the boundaries of what is possible, and to pursue knowledge and exploration for their own sake. The Breakthrough Starshot Initiative and other LightSail mission concepts thus represent not just technical proposals, but expressions of a broader vision of humanity's future among the stars. They suggest a path forward that, while challenging, appears to be within the realm of technological feasibility, offering the prospect of interstellar exploration within the lifetime of people living today. As we conclude our exploration of Project Starshot and LightSail missions, let us appreciate both the audacity of the vision and the practical, step-by-step approach being taken to realize it. The stars are distant, but not unreachable. With sustained effort, creative engineering, and collaborative international initiatives, humanity may yet take its first, tentative steps beyond our solar system toward the stellar neighbors that have beckoned us since the dawn of consciousness. The journey to the stars will not be easy or quick. It will require patience, persistence, and a commitment to long-term goals that transcend individual careers or even lifetimes. But the prospect of extending human presence, even in the form of tiny robotic emissaries, beyond the confines of our solar system, offers a compelling vision of our potential as a spacefaring species. Project Starshot and similar initiatives remind us that the exploration of space is not merely about technological achievement, but about expanding the horizon of human experience and understanding. Each step outward, from the first satellites in Earth orbit to the first footsteps on the Moon, from the first probes to other planets to the first spacecraft entering interstellar space, has not only advanced our scientific knowledge, but deepened our appreciation of our place in the cosmos. The next great step, sending spacecraft to other stars, awaits us. The technology is challenging, but not beyond our reach. The investment required is substantial, but not prohibitive. The time frame is measured in decades rather than years, but well within the span of a human life. With vision, commitment, and collaborative effort, we may yet see the first data from Alpha Centauri before the close of this century, opening a new chapter in humanity's engagement with the universe that surrounds us. As we look toward that future, let us consider not just what we might learn from such missions, but what they might mean for our self-understanding as a species. The ability to reach beyond our solar system, to touch other stars even in this modest way, would mark a new phase in human evolution, our emergence as a truly interstellar species. The light sails that might carry our first emissaries to the stars would serve not just as means of propulsion, but as symbols of human ingenuity, curiosity, and aspiration, unfurling in the vacuum of space like flags of exploration planted on a new frontier. As we contemplate voyages to the stars, a fundamental question emerges: should we send machines or people? This is not merely a technical consideration, but a question that touches on our deepest values, aspirations, and understanding of what it means to explore. In this chapter, we will examine the comparative advantages and challenges of human versus robotic interstellar travel, considering not only the technological feasibility but also the philosophical implications of each approach. The history of space exploration provides context for this discussion. In the early decades of the space age, there was often a tension between proponents of human spaceflight and advocates for robotic missions. Some, like the astronomer Thomas Gold, argued that the scientific return from robotic probes would be greater per dollar spent than from human missions. Others, including many of the astronauts themselves, maintained that the presence of human adaptability, creativity, and first-hand experience brought unique value that no machine could replicate. In practice, our exploration of space has involved a complementary mix of human and robotic missions. Humans have ventured as far as the Moon, while our robotic emissaries have visited every planet in our solar system, as well as numerous dwarf planets, asteroids, and comets. The International Space Station represents humanity's continuous presence in space for over 2 decades. While the Mars rovers have spent years exploring the red planet's surface with increasingly sophisticated autonomous capabilities, this hybrid approach has served us well within our solar system, where distances, while vast by terrestrial standards, still allow for communication delays measured in minutes or hours at most. But as we contemplate voyages to other stars, where one-way communication times would be measured in years or decades, the balance of considerations shifts dramatically. Let us begin by examining the case for robotic interstellar exploration. The most obvious advantage of sending machines, rather than humans, is mass. A robotic probe can be far smaller and lighter than a spacecraft designed to support human life. The Voyager probes, our first spacecraft to reach interstellar space, have a mass of about 800 kilograms each. By contrast, the International Space Station, which supports a crew of up to 7 astronauts in Earth orbit, has a mass of about 420,000 kilograms. This difference in mass has profound implications for propulsion requirements. The energy needed to accelerate a spacecraft to a given velocity is directly proportional to its mass. A human interstellar mission, with the life support systems, radiation shielding, food, water, and other supplies needed to sustain a crew for years or decades, would require vastly more energy for propulsion than a robotic probe designed to fulfill the same scientific objectives. This mass difference becomes even more significant when we consider the exponential relationship between the velocity change required for a mission and the propellant mass fraction, as described by the Tsiolkovsky rocket equation. For conventional rocket propulsion, the mass ratio grows exponentially with the desired change in velocity. For the extreme velocities needed for interstellar travel, a human mission with traditional propulsion would require a propellant mass so large as to be practically impossible. Alternative propulsion concepts, such as the light sails discussed in the previous chapter, are particularly sensitive to mass considerations. The acceleration produced by light pressure is inversely proportional to the mass of the spacecraft. The breakthrough Starshot concept, which aims to accelerate gram-scale probes to 20% of the speed of light using laser propulsion, simply could not be scaled up to accommodate human passengers without a corresponding increase in laser power far beyond what is currently feasible. Beyond propulsion, the life support requirements for human interstellar travel present enormous challenges. The crew would need a reliable supply of food, water, and oxygen for the duration of the journey, which would likely span decades or even centuries with foreseeable propulsion technology. While partial recycling of air and water has been demonstrated on the International Space Station, achieving the near-perfect closure of resource loops needed for interstellar journeys remains a formidable challenge. The psychological and social dimensions of such extended isolation also present significant obstacles. A crew confined to a spacecraft for decades would face stresses well beyond those experienced by astronauts on the International Space Station, who typically serve rotations of 6 months to a year. The effects of such long-term isolation and confinement on mental health, group dynamics, and mission performance are poorly understood, as we have no direct experience with comparable scenarios. Radiation exposure represents another serious challenge for human interstellar travel. Beyond the protective bubble of Earth's magnetic field, cosmic rays and solar radiation pose significant health risks to astronauts. On a journey of decades, the cumulative radiation dose could exceed safe lifetime limits unless substantial shielding is provided, adding further to the mass of the spacecraft. The medical support needed for a human interstellar mission would also be extensive. With no possibility of evacuation or resupply from Earth, the crew would need to be essentially self-sufficient in addressing any health issues that might arise over the course of decades. This would require not only extensive medical supplies and equipment, but also crew members with advanced medical training and the ability to perform complex procedures if necessary. Given these formidable challenges, robotic missions appear to be the more feasible approach to interstellar exploration, at least in the near term. Robotic probes can be designed to operate for decades without maintenance, to withstand radiation levels that would be harmful to humans, and to enter dormant or low-power modes for extended periods to conserve energy. They can be mass-produced for redundancy, allowing multiple probes to be sent toward the same destination, improving the odds that at least some will successfully complete the journey. Moreover, advances in artificial intelligence and autonomous systems are steadily increasing the capabilities of robotic explorers. The Mars rovers, for example, have evolved from the simple Sojourner rover of the 1990s, which could travel a few meters per day under close human supervision, to the Perseverance rover launched in 2020, which can navigate autonomously using sophisticated computer vision systems and make some decisions about scientific targets without human input. Extended to interstellar missions, this trend suggests that future robotic probes might possess levels of autonomy and adaptability approaching those of human explorers. They would need to, given the years-long communication delays that would make real-time control from Earth impossible. Such highly autonomous probes might be able to observe, analyze, and respond to unexpected discoveries in ways that early space probes could not, potentially capturing much of the adaptability that has historically been a key advantage of human exploration. Another advantage of robotic exploration is its potential for scalability and redundancy. Rather than sending a single, complex human mission, we could send dozens or hundreds of smaller robotic probes, each with slightly different instruments or targets. This swarm approach would not only increase the chances of mission success in the face of the many potential failure modes of interstellar travel, but would also allow for a broader range of scientific observations and greater collective capabilities than any single mission could provide. Despite these compelling advantages of robotic missions, the case for human interstellar travel is not merely sentimental or philosophical. Human presence brings unique capabilities and perspectives that may be difficult or impossible to replicate with machines, even highly advanced ones. Human sensory perception, for example, integrates multiple sensory modalities in ways that our most sophisticated sensors and algorithms still struggle to match. The ability of a human geologist to recognize interesting or unusual features in a landscape, to pick up a rock and intuitively assess its properties, or to notice subtle patterns that might not fit existing classification schemes, represents a level of perception and intuition that remains challenging for artificial systems to replicate. Similarly, human creativity and problem-solving abilities, particularly in novel or unexpected situations, still exceed those of our most advanced artificial intelligence systems. While AI has made remarkable progress in specific domains, such as chess, Go, and certain types of pattern recognition, it continues to struggle with the kind of open-ended, creative problem-solving that characterized, for example, the Apollo 13 mission, where astronauts and ground controllers improvised solutions to life-threatening problems not anticipated in mission planning. The human capacity for wonder, aesthetic appreciation, and meaning-making also brings a dimension to exploration that is difficult to quantify but nonetheless significant. When Buzz Aldrin described the lunar landscape as magnificent desolation, or when astronauts speak of the overview effect, the profound shift in perspective that comes from seeing Earth as a whole planet from space, they are expressing experiences that transcend mere data collection. There is also a symbolic and cultural dimension to human presence that robotic missions, however scientifically productive, cannot fully capture. The Apollo lunar landings, for example, remain iconic not just for their scientific return, but because they represented humanity's first steps on another world. The presence of people, as representatives of our species, brought a meaning and significance to these missions that resonated far beyond the scientific community. This symbolic dimension would be even more pronounced for interstellar travel. Having human beings actually present in another stellar system, experiencing and bearing witness to worlds around another sun, would represent a milestone in human history, comparable to the first sea voyages that circumnavigated the Earth or the first settlements in the Americas. It would mark our transition from a species confined to one star system to one with a presence around multiple stars, a profound expansion of the human frontier. Beyond these philosophical considerations, there are practical advantages to human presence in certain kinds of exploration and settlement scenarios. Humans have a remarkable ability to use and repair tools, to repurpose materials for unexpected needs, and to adapt plans in response to changing circumstances. These capabilities could be particularly valuable in establishing a long-term human presence around another star, where the goal is not just observation, but the creation of a sustainable human settlement. Given these complementary strengths and limitations of human and robotic exploration, it seems likely that our approach to interstellar missions will involve a synergy of both, much as our exploration of our own solar system has. However, the specific sequence and relationship between human and robotic missions may differ from our experience so far. In the context of interstellar travel, robotic missions will almost certainly precede human ones by a significant margin. The technical challenges of sending even small robotic probes to other stars are formidable. Those of sending human crews are orders of magnitude greater. It is reasonable to expect that we will have sent multiple generations of increasingly sophisticated robotic missions to nearby stars before the first human mission departs. These precursor robotic missions would serve multiple purposes. Most obviously, they would provide valuable scientific data about the target star systems, including detailed information about planets, moons, radiation environments, and potential resources. This information would be essential for planning any subsequent human missions, allowing them to be targeted to the most promising and hospitable destinations. Robotic precursors would also serve as technology demonstrations, validating propulsion, navigation, communication, and other systems needed for interstellar travel. Each successful mission would build confidence and experience, gradually reducing the risks of more ambitious subsequent missions. They would also establish the infrastructure, such as communication relays and navigation beacons, that would support later human missions. In this scenario, humans would eventually follow the path pioneered by robots, but only after multiple successful robotic missions had reduced the risks and uncertainties to acceptable levels. This approach parallels our exploration of the solar system, where robotic probes like the Ranger and Surveyor missions preceded the Apollo lunar landings, and where extensive robotic exploration of Mars is laying the groundwork for potential human missions in the coming decades. However, there is another possibility that deserves consideration. The robotic precursors to human interstellar missions might not be separate spacecraft, but integrated components of the human mission itself. Advanced robotic systems, perhaps guided by artificial intelligence, might be sent ahead to prepare the way, establish infrastructure, and reduce risks before human arrival. This concept of robotic precursors as components of a larger human mission, rather than separate enterprises, suggests a more integrated view of the relationship between human and machine in space exploration. Rather than seeing robots and humans as alternative or competing approaches, we might view them as complementary elements of a single exploration strategy, each contributing unique capabilities to a shared endeavor. Such integration is already evident in current space operations, where astronauts on the International Space Station work with robotic arms, autonomous supplies, vessels, and other mechanical systems as part of their daily activities. This synergy between human and machine is likely to deepen as artificial intelligence, robotics, and human-machine interfaces continue to advance. Looking further into the future, the distinction between human and robotic interstellar exploration might become even more blurred. Advances in neural interfaces, artificial intelligence, and biological engineering could lead to forms of space exploration that combine elements of both approaches in ways we can barely envision today. For example, human consciousness might someday be temporarily transferred to robotic bodies better suited to the extreme environments of other worlds, allowing human explorers to experience these environments directly without the physical vulnerability of biological bodies. Alternatively, highly advanced artificial intelligence systems might achieve levels of autonomy, adaptability, and even consciousness that make them more partners than tools in the exploration enterprise. While such possibilities remain speculative, they highlight the fact that our current categories of human and robotic exploration may not fully capture the range of approaches that might eventually become feasible. As technology evolves, so too will our understanding of what constitutes exploration and who or what can be considered an explorer. Returning to more near-term considerations, one concept that has received significant attention in discussions of human interstellar travel is the generation ship, This approach acknowledges the likely reality that with foreseeable propulsion technology, interstellar journeys would take centuries or millennia, far exceeding a human lifespan. Rather than trying to extend individual lifespans to match journey times, the generation ship concept envisions a self-contained habitat carrying a community of people, with the understanding that it would be the descendants of the original crew, perhaps many generations later, who would arrive at the destination. Such a vessel would need to be essentially a miniature world, with closed ecological systems recycling air, water, and nutrients with near-perfect efficiency. It would need to provide for the physical and psychological well-being of its inhabitants across generations, maintaining a viable society and culture over timescales longer than any civilization in human history has remained stable. The challenges of creating such a closed, self-sustaining system are formidable. Experiments like Biosphere 2, which attempted to create a closed ecological system on Earth in the 1990s, encountered numerous difficulties, from oxygen depletion to maintenance of biodiversity. Scaling such systems to support a genetically viable human population over centuries would represent an enormous engineering and ecological challenge. The social and cultural dimensions of generation ships present equally significant challenges. How would a society confined to a vessel maintain cohesion, purpose, and cultural continuity over centuries? How would it govern itself? How would it preserve the knowledge and skills needed to complete the mission while allowing for cultural evolution and adaptation over time? How would it prevent the mission's original purpose from being forgotten or discarded by later generations? These questions have no easy answers and point to the profound social engineering challenges that would accompany the technical ones in any generation ship mission. They also highlight the ethical questions surrounding such a venture. Do we have the right to commit future generations, not yet born, to lives constrained within a spacecraft, with no choice about their participation in the mission? An alternative to generation ships that has received considerable attention in both scientific and science fiction literature is suspended animation or hibernation. This approach would aim to drastically reduce human metabolic activity during the journey, effectively pausing biological time for the travelers until they reach their destination. Various mechanisms for achieving such suspended animation have been proposed, from cryogenic freezing to induced torpor states similar to those observed in hibernating animals. Limited forms of metabolic reduction through hypothermia are already used in certain medical procedures, but extending such techniques to the years or decades required for interstellar travel remains speculative. The advantages of successful suspended animation technology for interstellar travel would be substantial. It would allow the original crew to experience the entire journey, eliminating the social and ethical complexities of generation ships. It would reduce life support requirements during the cruise phase, as hibernating crew members would require minimal food, water, and oxygen. And it would allow mission planners to select and train a crew specifically for the destination activities, rather than relying on the training and preparation of generations removed from the mission's origin. However, suspended animation for interstellar timeframes faces significant biological and technical hurdles. Long-term metabolic suppression would need to address issues of cellular damage, waste product accumulation, muscle and bone atrophy, and many other physiological challenges. The technology would need to be extraordinarily reliable, as a failure of the hibernation systems during the journey could be fatal with no possibility of external intervention. A third approach to human interstellar travel that has gained attention in more recent discussions is the concept of digital emulation or mind uploading. This speculative technology would involve scanning the structure and connectivity of a human brain in sufficient detail to create a digital copy or emulation of the person's mind, which could then be instantiated in a computer system, or, upon arrival at the destination, in a new biological or robotic body. Such digital travelers would not face the biological limitations of traditional human explorers. They would not require air, water, food, or protection from radiation. They could potentially be transmitted as data at the speed of light, though this would still mean years of travel time to reach even the nearest stars. They could exist in dormant states for extended periods, activated only when needed or upon arrival at the destination. The philosophical and ethical questions raised by such digital emulation are profound. Would a digital copy of a person's mind, with all their memories and personality, be the same person in a meaningful sense? If the original person continued to live on Earth while their digital copy explored another star system, which would be the real person, would such digital existence constitute a form of immortality, or would it be a fundamentally different kind of existence? These questions touch on deep issues of consciousness, identity, and what it means to be human, issues that philosophy and science have grappled with for centuries and that remain unresolved. They highlight the fact that advanced technologies for interstellar travel might not just extend our physical reach, but could potentially transform our understanding of ourselves in fundamental ways. As we consider these various approaches to human interstellar travel, generation ships, hibernation, and digital emulation, it is worth noting that they are not mutually exclusive. A human interstellar mission might combine elements of all three, with some crew members in suspended animation, others living normal lifespans as part of a multi-generational crew, and still others existing as digital emulations, each contributing unique capabilities to the mission. This hybrid approach might offer redundancy and resilience, with different modes of human presence serving as backups for each other. It might also allow the mission to leverage the unique advantages of each approach, creating a more robust and adaptable human presence than any single method could provide. Regardless of the specific approach, human interstellar travel would represent a profound milestone in our evolution as a spacefaring species. It would mark our transition from a civilization bound to a single star system to one with a presence around multiple stars. It would potentially serve as a form of species-level insurance, ensuring that humanity would continue even if some catastrophe befell Earth or our solar system. The establishment of human settlements around other stars would also create the conditions for a new phase of cultural and potentially biological evolution. Separated by the light years between stars, these settlements would inevitably develop their own distinct societies, technologies, and perhaps even new forms of humanity adapted to their specific environments. This divergence would not necessarily be a fragmentation, but could be viewed as an enrichment of human diversity, a blossoming of different forms of human culture and experience across multiple worlds. Just as the separation of human populations on Earth led to the rich tapestry of human languages, societies, and adaptations, so too might interstellar separation lead to a flourishing of different expressions of humanity among the stars. In contrast to this grand vision of human expansion beyond our solar system, robotic exploration offers a more modest, but also more feasible, near-term approach. Rather than attempting to transplant human life to other star systems, it focuses on extending our perception and understanding through mechanical proxies. This approach aligns with a perspective that values observation and knowledge over physical presence, that sees the universe primarily as something to be studied and appreciated, rather than inhabited and transformed. It suggests a more gentle, less transformative engagement with the cosmos, one that satisfies our curiosity, while leaving other star systems largely as we found them. There is a philosophical richness to this perspective that should not be dismissed. The ability to observe and understand the universe without necessarily reshaping it to our purposes represents a kind of maturity and restraint. It acknowledges that our primary relationship with the cosmos might be one of wonder and learning rather than occupation and utilization. Moreover, advanced robotic explorers might eventually blur the distinction between observation and experience in ways we cannot currently foresee. If, for example, virtual reality technologies advance to the point where they can convincingly simulate the experience of standing on a world orbiting another star, based on data from robotic probes, would this not satisfy much of the human yearning for direct experience of other worlds? Similarly, if artificial intelligence advances to the point where robotic probes possess consciousness and self-awareness comparable to human beings, would their exploration of other star systems not constitute a form of sentient experience of the cosmos, even if not specifically human experience? These possibilities suggest that the categories of human and robotic exploration might eventually converge or transcend their current meanings. As we weigh these different approaches to interstellar exploration, human and robotic, it is important to remember that they need not be viewed as competing alternatives, but as complementary components of a broader human engagement with the cosmos. Each offers unique advantages and limitations, each aligns with different values and priorities, and each may find its place in our future as a spacefaring species. In the near term, robotic missions appear to be the most feasible approach to interstellar exploration, Their lower mass, greater tolerance for radiation and extreme environments, and potential for redundancy through multiple launches make them better suited to the formidable challenges of interstellar travel with current or near-future technology. Looking further ahead, as propulsion technology, life support systems, and our understanding of closed ecological systems advance, human interstellar travel may become more feasible. When it does, it will build upon the foundation laid by robotic precursors, leveraging their discoveries and the technologies they helped to validate. The relationship between human and robotic exploration may thus be viewed not as a competition, but as a partnership, with each approach contributing to a shared endeavor of expanding human understanding and, potentially, human presence beyond our solar system. This partnership is already evident in our exploration of our own solar system, where human and robotic missions complement and support each other, and it is likely to continue as we set our sights on the stars. As we conclude our exploration of the comparative advantages and challenges of human versus robotic interstellar travel, let us appreciate the richness of possibilities that lie before us. Whether through mechanical proxies, biological presence, digital emulation, or some combination of these approaches, humanity's engagement with the cosmos beyond our solar system represents an extraordinary chapter in our evolution as a species. The stars have beckoned to us throughout human history, inspiring wonder, curiosity, and aspiration. Now, as our technological capabilities begin to approach the threshold where interstellar exploration becomes feasible, we face profound choices about how to approach this next great frontier. These choices reflect not just technical considerations but our deepest values, our understanding of our place in the cosmos, and our vision of what humanity might become. Whether our first emissaries to the stars are robots or humans, digital minds or biological ones, they will carry with them the accumulated knowledge, creativity, and aspirations of our species. And in their journey, they will transcend the boundaries that have defined human existence since our emergence as a species, venturing beyond the protective cradle of our home solar system into the vast cosmic ocean that surrounds us. As we contemplate voyages to nearby stars, perhaps the most compelling question is, what awaits us there? What worlds might orbit these neighboring suns? Could they harbor environments remotely similar to Earth, or perhaps life forms utterly unlike anything we know? In this chapter, we will explore the current state of knowledge about exoplanets, particularly those in nearby stellar systems, and consider the range of possibilities that future interstellar missions might encounter. Our understanding of planetary systems beyond our own has undergone a revolution in recent decades. Before 1995, we had no confirmed discoveries of planets orbiting sun-like stars. Astronomers had theoretical models suggesting that planets might be common, but no direct evidence. Today, we have confirmed the existence of over 4,000 exoplanets, with thousands more candidates awaiting verification. This explosion of discovery has transformed our view of our place in the cosmos, revealing that planetary systems are not rare exceptions but common features around stars throughout our galaxy. Several methods have contributed to this wealth of discoveries. The transit method detects the slight dimming of a star's light when a planet passes in front of it from our perspective. This approach has been particularly productive for the Kepler Space Telescope and its successor, TESS, the Transiting Exoplanet Survey Satellite. The radial velocity method, also known as the Doppler wobble technique, detects the subtle motion of a star caused by the gravitational pull of its planets. Direct imaging, which captures actual images of planets, has succeeded for a small number of large planets far from their stars. Gravitational microlensing, which detects planets through their gravitational effects on light from background stars, has revealed planets in more distant parts of our galaxy. Each of these methods has different strengths and biases. The transit method works best for large planets orbiting close to their stars, as these create more significant dimming. The radial velocity method is most sensitive to massive planets, as they induce larger stellar wobbles. Direct imaging favors large, young, hot planets orbiting far from their stars, where they are easier to distinguish from the stellar glare. These biases mean that our current census of exoplanets is incomplete, with some types of planets, particularly those similar to Earth in size and orbit, still underrepresented in our data. Despite these limitations, the wealth of exoplanet discoveries has revealed surprising diversity in planetary systems. We have found hot Jupiters, gas giants, orbiting closer to their stars than Mercury does to our Sun, a configuration not seen in our solar system. We have discovered super-Earths and mini-Neptunes, planets with sizes between Earth and Neptune that have no counterpart in our solar system. We have found systems with multiple planets packed into orbits closer to their star than Mercury's orbit, and others with planets in highly elliptical orbits, unlike the nearly circular paths of planets in our system. This diversity suggests that planetary formation and evolution follow multiple pathways, influenced by factors such as the initial properties of the protoplanetary disk, interactions between forming planets, and the effects of nearby stars or other cosmic events. Our solar system, once the only example we knew, appears to be just one possibility among many, perhaps not even the most common arrangement. Of particular interest for potential interstellar missions are the planetary systems around our nearest stellar neighbors. The Alpha Centauri system, just over 4 light-years away, consists of 3 stars, Alpha Centauri A and B, which orbit each other as a binary pair, and Proxima Centauri, a small red dwarf orbiting much farther out from the main pair. In 2016, astronomers announced the discovery of Proxima Centauri b, a planet orbiting within the habitable zone of Proxima Centauri. This world, with a minimum mass of about 1.3 times that of Earth, orbits its star every 11.2 days at a distance of just 7.5 million kilometers. Despite this close proximity to its star, Proxima b receives about the same amount of energy as Earth does from the Sun, because Proxima Centauri is much smaller and dimmer than our Sun. The discovery of a potentially habitable world around the very nearest star to our solar system was a remarkable coincidence and a tantalizing target for future exploration. However, habitability is a complex question that depends on many factors beyond just the amount of stellar energy a planet receives. One significant concern for planets orbiting red dwarf stars like Proxima Centauri is tidal locking. When a planet orbits very close to its star, tidal forces tend to slow its rotation until one side perpetually faces the star, similar to how the same side of the Moon always faces Earth. This creates a world of permanent day on one hemisphere and permanent night on the other, with a twilight zone in between. Such a dramatic temperature differential could create extreme weather, with powerful winds blowing continuously from the hot side to the cold side. Water might evaporate on the star-facing side and freeze out on the night side, potentially rendering the planet uninhabitable. However, atmospheric circulation, if substantial enough, could potentially moderate these extremes, allowing for a more temperate environment, particularly in the twilight regions. Another concern for planets around red dwarf stars is stellar activity. Red dwarfs, especially young ones, are prone to powerful flares that emit intense ultraviolet and X-ray radiation. Proxima Centauri, despite being an estimated 4.8 billion years old, similar to our Sun, remains quite active. In 2016, astronomers observed a flare that briefly made Proxima 60 times brighter in the ultraviolet spectrum. Such events, if common, could strip away a planet's atmosphere over time and bathe its surface in radiation harmful to life as we know it. However, not all hope is lost for potential habitability. If Proxima b formed with a substantial inventory of water and other volatiles, and if it generated a magnetic field strong enough to deflect some of the stellar particles, it might retain an atmosphere despite the stellar activity. The planet's mass, somewhat larger than Earth's, suggests it might indeed have a stronger magnetic field than our planet, though this remains speculative without direct measurements. In 2020, astronomers announced the discovery of a second planet orbiting Proxima Centauri. Designated Proxima c, this world is estimated to have a mass about 7 times that of Earth, placing it in the super-Earth or mini-Neptune category. It orbits much farther out from the star, at a distance of about 1.5 astronomical units, completing one orbit in about 5 years. At this distance, the planet is likely too cold for liquid water on its surface, though subsurface oceans, heated by internal processes, remain a possibility. The main pair in the Alpha Centauri system, stars more similar to our Sun, have also been targets of intense planet hunting efforts. In 2012, astronomers announced the discovery of a planet orbiting Alpha Centauri b, but this claim was later retracted when further analysis showed the signal was likely an artifact of the data analysis method. As of now, no confirmed planets have been detected around either Alpha Centauri A or B, but the search continues with ever more sensitive instruments. The lack of confirmed discoveries does not mean these stars are without planets. The current detection methods have limitations, particularly for finding Earth-sized planets in Earth, like orbits around Sun-like stars. Such worlds would create very small signals in both transit and radial velocity measurements, requiring extremely precise observations over extended periods. Future observations, both from ground-based telescopes and from space-based instruments like the James Webb Space Telescope, may yet reveal planets around the main Alpha Centauri stars. Beyond the Alpha Centauri system, our next nearest stellar neighbor is Barnard's star, about 6 light-years away. In 2018, astronomers announced the discovery of a planet orbiting this small red dwarf. Barnard's star B has a mass of at least 3.2 times that of Earth and orbits at a distance similar to Mercury's orbit around our Sun. Despite this relatively close orbit, the planet receives only about 2% of the energy that Earth receives from the Sun, making its surface likely frozen, with an estimated temperature of about -170 degrees Celsius. While such a cold world seems unpromising for habitability, it is worth noting that subsurface oceans exist within icy moons in our solar system, such as Europa and Enceladus, warmed by internal processes rather than direct stellar heating. Similar environments could potentially exist on Barnard's star B, though confirming this would require direct exploration. TRAPPIST-1, a small, cool star about 40 light-years away, represents another intriguing nearby system. Astronomers have discovered 7 Earth-sized planets orbiting this star, 3 of which lie within the traditional habitable zone. These planets orbit very close to their star, with years ranging from 1.5 to 20 Earth days. Like planets around Proxima Centauri, they likely face challenges from tidal locking and stellar activity, but the presence of multiple Earth-sized worlds in a single system makes TRAPPIST-1 a compelling target for future studies. As we look to more distant stars within about 20 light-years, we find additional promising systems. Tau Ceti, a Sun-like star about 12 light-years away, hosts at least 4 planets, including 2 that may lie within the habitable zone. These super-Earths, with masses between about 1.7 and about 4 times that of Earth, orbit a stable, inactive star that is often cited as one of the most Sun-like in our neighborhood. However, Tau Ceti also possesses a substantial debris disk, containing about 10 times as much material as our Sun's asteroid belt. This abundance of potentially impacting objects could present challenges for the development of life on any planets in the system, as frequent large impacts might disrupt evolutionary processes. The diversity of these nearby planetary systems suggests that interstellar missions might encounter a wide range of worlds, from scorching hot planets hugging their stars to frozen worlds far from stellar warmth, from rocky planets like Earth to gas giants like Jupiter, and every variation in between. This diversity presents both challenges and opportunities for exploration, requiring flexible mission designs capable of studying various types of planets and planetary environments. What might these worlds look like up close? For rocky planets, the appearance would depend on many factors, including the planet's mass, composition, atmospheric density, and distance from its star. A world somewhat larger than Earth might have stronger gravity, potentially leading to a flatter landscape with lower mountains and shallower ocean basins, assuming it has comparable geological processes and water content. The color of the sky would depend on the composition of the atmosphere and the spectrum of the parent star. Our blue sky results from the scattering of sunlight by nitrogen and oxygen molecules, which preferentially scatter blue wavelengths. A planet with a different atmospheric composition, or orbiting a star with a different spectral distribution, might have a sky of another color, perhaps the rusty hue of Mars, or something entirely unfamiliar. The presence and appearance of water would be a critical factor in a planet's habitability and visual character. Earth's blue oceans are one of its most distinctive features when viewed from space. A planet with more water might appear almost entirely blue, with minimal land masses, while one with less might show more continental features. The distribution of land and water would influence climate patterns, potentially creating zones of habitability even on worlds that are, on average, too hot or too cold for Earth-like conditions. The nature of any plant life would also significantly influence a planet's appearance. On Earth, chlorophyll, which absorbs red and blue light while reflecting green, gives our vegetation its characteristic color. However, around stars with different spectral distributions, photosynthetic organisms might evolve to use different pigments, optimized to capture the available light. Around red dwarf stars, which emit more of their energy in the infrared, plants might be black to absorb across the spectrum, or reflect different wavelengths, appearing red, yellow, or even colors outside our visual range. For gas giants, the appearance would depend on atmospheric composition, temperature, and weather patterns. Jupiter's distinctive bands and Great Red Spot result from complex flow patterns in its atmosphere, combined with chemical reactions that create colorful compounds. Gas giants around other stars might display similar features, though with variations based on their specific conditions. Ice worlds, like those we might find in the outer regions of stellar systems, might resemble some of the moons of our outer solar system, such as Europa or Enceladus. These could have surfaces of water, ice, potentially covering subsurface oceans, kept liquid by internal heating from radioactive decay or tidal flexing. Such worlds might appear relatively bland from orbit, with white or off-white surfaces marked by cracks and other features, but could harbor complex environments, and potentially even life, beneath their frozen exteriors. Beyond the visible appearance of these worlds, future interstellar missions would seek to characterize their physical properties, atmospheric compositions, geological activities, and, perhaps most tantalizingly, any signs of life. For rocky planets with atmospheres, spectroscopic observations could reveal the presence of gases like oxygen, methane, or carbon dioxide, providing insights into the planet's composition and potential habitability. The detection of certain combinations of gases, such as the simultaneous presence of oxygen and methane at significant levels, could suggest biological activity, as these gases would react with each other unless continuously replenished. Such biosignature gases are a major focus of exoplanet research, offering the possibility of detecting life on distant worlds without direct physical exploration. However, the interpretation of atmospheric data is complex and potentially ambiguous. Non-biological processes can produce many of the same gases as biological ones, creating the risk of false positives. Conversely, life forms with biochemistries different from those on Earth might produce different waste products, creating the possibility of false negatives if we search only for Earth-like biosignatures. This highlights a broader challenge in the search for extraterrestrial life: the tension between the need to focus on the one example of life we know, that of Earth, and the recognition that life elsewhere might take forms we have not considered. This tension has led to ongoing debates in astrobiology about how broadly to define life, what biosignatures to prioritize in our searches, and how to design missions that balance the focused search for Earth-like life with the openness to more exotic possibilities. For nearby star systems, future space telescopes may be able to directly image planets and analyze their atmospheres, providing a wealth of information before any interstellar probe arrives. However, there will always be limitations to what we can observe from a distance of light years. Direct exploration, even by small robotic probes, could potentially reveal details about geological features, weather patterns, magnetic fields, and other characteristics that cannot be discerned through remote observation. Perhaps the most exciting prospect is the possibility of discovering life beyond Earth. The presence of liquid water, which appears to be a requirement for all life on our planet, seems possible on several worlds in nearby systems, particularly Proxima Centauri b and the habitable zone planets of TRAPPIST-1. If life has emerged on any of these worlds, it would provide a second data point beside Earth, allowing us to begin distinguishing between the universal and contingent aspects of biology. The discovery of even microbial life beyond our solar system would have profound implications for our understanding of life's prevalence in the universe. If life has emerged independently in two stellar systems within just a few light years of each other, it would suggest that life might be a common outcome of planetary formation, potentially abundant throughout our galaxy and beyond. Conversely, If we find that even potentially habitable worlds in nearby systems are sterile, it might suggest that the emergence of life requires special conditions or fortunate circumstances beyond just the presence of liquid water. This, too, would be a significant finding, helping to constrain our estimates of how many worlds in our galaxy might host life. Should we discover life on exoplanets, one of the most intriguing questions would be how similar or different it is to life on Earth. Would it use DNA or something analogous as its genetic material? Would it be based on carbon chemistry and liquid water, as all known life on Earth is? Would it use similar metabolic processes, capturing energy from its environment through mechanisms like photosynthesis or chemosynthesis? On one hand, the basic chemistry that underlies life on Earth, with carbon forming the backbone of complex organic molecules dissolved or suspended in water, has certain advantages that might make it a common solution. Carbon's ability to form 4 bonds allows for the creation of incredibly diverse and complex molecules. Water serves as an excellent solvent for these molecules, with properties like its wide liquid temperature range, high heat capacity, and ability to facilitate many chemical reactions. On the other hand, even within the constraints of carbon-based, water-solvent life, there is room for enormous variation. Consider the diversity of life on Earth, from bacteria that can survive in near boiling acid to fungi that digest rock, from plants that derive energy from sunlight to animals that hunt and consume other organisms, from organisms that require oxygen to those that are poisoned by it. This diversity emerged from a single origin of life on our planet. Independent origins elsewhere could potentially lead to even greater differences. More exotic possibilities include life based on silicon rather than carbon, which could form similar complex molecules although with different properties. Alternative solvents might include ammonia, which is liquid at much lower temperatures than water, or even more exotic substances like liquid methane or hydrogen, though these would require very different biochemistries adapted to these environments. Rather than speculating on specific forms, it may be more productive to consider the general characteristics that life might share across different worlds. These could include the ability to maintain internal conditions different from the external environment, to extract energy from the environment to power metabolism, to grow and reproduce, to evolve through some mechanism of variation and selection, and to respond to environmental stimuli. Life adapted to the conditions on planets around red dwarf stars might have evolved unique features to cope with the challenges of these environments. On tidally locked planets like Proxima Centauri b, organisms might have adapted to the permanent day side, permanent night side, or the twilight zone in between, each presenting different challenges and opportunities. Plants or their equivalents on the day side might need protection from the constant stellar radiation, perhaps growing close to the ground or underwater to shield themselves. They might also need mechanisms to cope with the powerful winds that could result from the temperature differential between the day and night sides. Organisms on the night side would face perpetual darkness and cold, perhaps evolving chemosynthetic or other non-photosynthetic metabolisms, or migrating in from the more hospitable twilight regions. Life on planets subject to frequent stellar flares might have evolved robust mechanisms to repair radiation damage or to retreat to protected environments during flare events. Underground habitats, deep oceans, or even hibernation during periods of intense stellar activity could be adaptations to such conditions. For planets around Sun-like stars, such as any that might be discovered in the Alpha Centauri A and B system or around Tau Ceti, conditions might be more similar to those on Earth, potentially allowing for more familiar forms of life. However, differences in factors like gravity, atmospheric composition, or the length of the day and year could still lead to significant adaptations. Higher gravity worlds might favor shorter, more robust organisms with stronger skeletal structures or exoskeletons. Lower gravity might allow for taller, more delicate forms, possibly including flying creatures larger than any found on Earth. Different atmospheric compositions could lead to varied respiratory systems, with organisms adapted to extract oxygen or other electron acceptors from their environment through mechanisms unlike those of Earth life. Beyond the physical characteristics of any life forms, an even more speculative but fascinating area to consider is the potential for intelligent life. The emergence of human-level intelligence on Earth was the result of a complex evolutionary history, influenced by myriad factors from environmental pressures to chance events like asteroid impacts. Whether similar intelligence would evolve on other worlds is a profound open question in astrobiology and evolutionary theory. Some scientists argue that intelligence, particularly the kind that develops technology, may be a rare outcome, even among worlds with life. They point to the billions of years life existed on Earth before human intelligence emerged, and to the fact that of the millions of species that have existed on our planet, only one has developed technologies like agriculture, writing, or spaceflight. Others suggest that intelligence, while not inevitable, might be a relatively common adaptation given enough time and the right conditions. They note that multiple lineages on Earth, from cetaceans to cephalopods to various bird species, have independently evolved relatively high intelligence, suggesting it may be a valuable trait in many ecological contexts. If intelligent life does exist around nearby stars, it might be detectable through technosignatures, signs of technology that could include radio emissions, large-scale modification of its environment, or other artifacts of civilization. However, the absence of such detections so far in our astronomical observations, a phenomenon known as the Fermi paradox, suggests that technological civilizations may be rare, short-lived, or difficult to detect at our current level of technology. The discovery of any form of life beyond Earth, whether microbial or intelligent, would be one of the most significant scientific discoveries in human history. It would provide context for our own existence, helping us understand whether life is a common outcome of cosmic processes or a rare phenomenon in an otherwise sterile universe. This knowledge would have profound implications not just for science, but for philosophy, religion, and our understanding of our place in the cosmos. Of course, we must also consider the possibility that the nearest star systems, despite having potentially habitable planets, may be devoid of life. Perhaps the emergence of life requires specific conditions or sequences of events that are relatively rare, or perhaps life is common but has not yet had time to emerge on nearby worlds. The universe is still in its youth relative to how long it will remain habitable, and our Sun is a third-generation star, formed from the remains of earlier stellar generations. It is possible that life on Earth got a relatively early start compared to the cosmic average. Even the discovery that nearby potentially habitable worlds are sterile would be scientifically valuable, helping to constrain our models of life's origins and prevalence. Moreover, such worlds might one day become homes for life from Earth, whether in the form of human settlements or deliberate seeding with Earth organisms in a process sometimes called terraforming. The ethical implications of such an endeavor would be complex and would depend significantly on what we find in these systems. If a world is truly sterile, with no indigenous life forms to displace or harm, the argument for terraforming might be relatively straightforward, though still subject to debate about whether humans have the right to so dramatically alter another world. If we find existing life, particularly if it represents an independent origin from Earth life, the ethical calculus becomes much more complex. Most scientists and ethicists would argue for preserving and studying such life, rather than potentially displacing it with Earth organisms. The discovery of a second genesis of life would be so scientifically valuable that contaminating or endangering it for human benefit would be difficult to justify. As we send our first robotic emissaries to nearby stars, likely in the form of small, fast-moving probes, like those envisioned by Breakthrough Starshot, we will begin to get direct observations that will help answer some of these questions. These initial missions will be limited in their capabilities, capturing perhaps a few images and basic measurements as they fly through their target systems. But even these limited data would provide our first close-up view of another stellar system, potentially including direct imaging of exoplanets. Subsequent missions, perhaps larger and more capable but still robotic, might follow, building on the knowledge gained from the first wave of exploration. Eventually, if the technical challenges can be overcome, human missions might venture to nearby stars, bringing the full range of human observation, creativity, and adaptability to the exploration of these distant worlds. What we find there, whether barren but fascinating worlds, simple microbial life, or even complex ecosystems, will shape humanity's future among the stars. The knowledge we gain will inform decisions about where and how to establish settlements beyond our solar system, if we choose to do so. It will influence our understanding of biology, planetary science, and astronomy, potentially leading to new fields of study focused on comparing different worlds and their inhabitants, if any. The nearest stars have shone in our night sky throughout human history, their light traveling years to reach our eyes. Soon, we may send our own emissaries to follow that light back to its source, extending human perception, and perhaps eventually human presence, to these neighboring stellar systems. What we find there will not only answer long-standing scientific questions, but may well shape the long-term future of our species. As we gaze at these stars in our night sky, let us remember that they are not merely points of light but places, with their own planets, moons, and possibly even life forms. Whether these distant worlds turn out to be broadly similar to those in our solar system, or startlingly different, whether they harbor life or are sterile, they represent the next great frontier of human exploration and discovery. The journey to these stars, and the discovery of what awaits us there, is the next chapter in the grand human adventure of exploration that has taken us across oceans, to the poles of our planet, and throughout our solar system. As we prepare to take this next great step outward, we carry with us the curiosity, wonder, and determination that have characterized human exploration throughout our history, now directed toward the most distant shores we have yet attempted to reach. As we contemplate voyages to distant stars, we naturally focus on the technological challenges, the scientific discoveries, and the potential wonders that await us in these far-flung stellar systems. Yet perhaps equally profound are the ways in which these interstellar journeys might transform us, not just as individuals or societies, but as a species. In this chapter, we will explore how the endeavor of reaching the stars might change humanity, both during the journey and in the long-term aftermath of establishing a multi-stellar presence. The impact of deep space and truly vast distances on the human psyche represents our first consideration. Even within our solar system, astronauts have reported profound psychological effects from seeing Earth as a small, fragile sphere suspended in the blackness of space. This perspective shift, often called the overview effect, has led many space travelers to a deepened sense of connection to humanity as a whole and a heightened awareness of the preciousness of our planetary home. Imagine, then, the psychological impact of a journey where Earth not only appears as a small blue dot but eventually becomes indistinguishable from the background stars. On an interstellar voyage, travelers would experience a level of separation from Earth unprecedented in human experience. The home planet, with all its familiar landmarks, weather patterns, and day-night cycles, would be replaced by the artificial environment of a spacecraft or habitat. Communication with Earth would be subject to delays of years or decades, making real-time conversation impossible and creating an unprecedented form of isolation. This profound separation would likely induce psychological and cultural changes among interstellar travelers. Cut off from the immediate influence of Earth's societies and cultures, they would inevitably develop their own customs, values, and perhaps even language variations. New art forms might emerge, inspired by the unique experiences of interstellar travel and the environments encountered along the way. Social structures might evolve to adapt to the constraints and opportunities of life aboard a generation ship or in a new stellar system. The history of human exploration on Earth offers some parallels for this process of cultural divergence. When groups of humans migrated to new territories, especially when geographic barriers limited contact with their origins, they typically developed distinct cultures adapted to their new environments. Languages diverged into separate dialects and eventually into mutually unintelligible tongues. Religious practices, social structures, and technological approaches all evolved in response to new challenges and opportunities. Interstellar travel would represent this process taken to an extreme, with physical distances far greater than any on Earth and communication delays that would make cultural exchange extraordinarily slow. The results could be a blossoming of human cultural diversity far beyond what we have seen on our home planet, with each stellar system potentially developing its own distinct branch of human civilization. This cultural divergence might be accompanied by biological changes as well, particularly for settlements established around other stars. Different gravity levels, radiation environments, day-length cycles, and available resources would create selection pressures unlike those on Earth. Over generations, human populations living under these conditions might develop adaptations, whether through natural selection, or perhaps more likely, through deliberate genetic modification to better suit their new homes. Such biological divergence would raise profound questions about human identity and unity. At what point would adaptations to different stellar environments create populations so different from Earth humans that they might be considered different species? How would we maintain a sense of shared humanity across such potentially vast biological and cultural differences? These questions have no easy answers, but would become increasingly relevant as interstellar settlement proceeded. Beyond these long-term transformations of interstellar societies, the very act of preparing for and undertaking such journeys would likely change those remaining on Earth as well. The enormous technological challenges of interstellar travel would drive innovation across multiple fields, from propulsion and materials science to closed-loop life support and advanced computing. These innovations would likely find applications beyond space travel, potentially transforming life on Earth in ways we can barely imagine. Consider the advances in computing, materials, miniaturization, and communications that emerged from the Apollo program and later space initiatives. These technologies found their way into countless everyday applications, from the smartphones in our pockets to the lightweight materials in our vehicles. An interstellar program, requiring advances orders of magnitude beyond current capabilities, might similarly seed technologies that transform human society even before the first mission departs. The societal organization required for such an enormous undertaking would also have transformative effects. Interstellar missions, whether human or robotic, would require sustained commitment across decades or centuries, transcending the typical timeframes of political and economic planning. This need for long-term thinking and commitment might drive the development of new institutions and decision-making frameworks designed to maintain focus on multi-generational projects. Such institutional innovations could have applications well beyond space exploration. Many of the most pressing challenges facing humanity, from climate change to sustainable resource management, require planning and commitment on timeframes longer than traditional political cycles. Frameworks developed to enable interstellar missions might provide models for addressing these terrestrial challenges as well. The philosophical and spiritual dimensions of interstellar travel may be as significant as the technological and sociological ones. Throughout human history, our understanding of our place in the cosmos has shaped our philosophies, religions, and worldviews. The Copernican revolution, which demonstrated that Earth is not the center of the universe, required profound adjustments in how humans viewed their place in creation. The Darwinian revolution, revealing our evolutionary kinship with all life on Earth, similarly transformed our self-conception. Interstellar travel would represent another such transformative step in our cosmic understanding. By directly exploring other stellar systems, we would gain a visceral, experiential perspective on our place in the galaxy that no amount of telescopic observation could provide. The potential discovery of life beyond our solar system, whether microbial or more complex, would provide context for understanding life on Earth, helping us distinguish between the universal aspects of biology and those unique to our home planet. Even in the absence of discovering extraterrestrial life, the direct experience of other worlds, orbiting other suns, would likely transform our perspective. The vast diversity of planetary environments, each shaped by its own unique history and conditions, would highlight both the preciousness of Earth's biosphere and the potential for human adaptation and flourishing in environments very different from our evolutionary home. This expanded cosmic perspective might foster a deepened sense of responsibility for the long-term future of humanity and life originating from Earth. As the only known technological species in our corner of the galaxy, we would bear the responsibility for carrying the torch of consciousness and intelligence beyond our solar system. This awareness might encourage a more mature relationship with technology, using it not just for short-term benefit but as a means of ensuring the long-term flourishing of consciousness in our galaxy. The practical challenges of interstellar travel would also force us to confront fundamental questions about human identity and continuity. Generation ships, where multiple generations would live and die during the journey, raise questions about the meaning of consent and choice, when decisions made by one generation constrain the options of their descendants. Suspended animation or hibernation technologies, if developed, would create their own ethical dilemmas about the extension of human lifespans and the potential creation of extreme disparities in lived experience and cultural context between those who sleep through centuries and those who remain awake. Perhaps most profound would be the potential development of digital emulation or mind-uploading technologies, which might allow human consciousness to be transferred to computational substrates. Such technology, if realized, would represent a transformation of human existence, at least as significant as the transition from single-celled to multicellular life, or from non-linguistic to linguistic thought. It would raise fundamental questions about what it means to be human, what constitutes personal identity, and how consciousness relates to its physical substrate. These existential and philosophical dimensions of interstellar travel highlight an important truth. The journey to the stars is not merely an outward exploration of physical space, but an inward journey of human self-discovery and transformation. As we reach toward other suns, we are simultaneously reaching toward new understandings of ourselves, our place in the cosmos, and our potential futures as a species. This dual nature of exploration, as both outward and inward journey, has precedent in human history. The age of maritime exploration, which saw European vessels circumnavigate the globe and establish contact with previously unknown, to them, civilizations, transformed not just the practical realities of global trade and politics, but the self-conception of the exploring cultures. Exposure to different societies, technologies, and worldviews forced a re-evaluation of assumptions previously taken for granted. Interstellar exploration would represent this process at a far greater scale. The potential discovery of independently evolved life would provide perspective on Earth life's contingent features. Encountering worlds in vastly different stages of evolution would contextualize Earth's history and possible futures. The experience of truly cosmic distances and timescales would reframe our understanding of human history and destiny. Even the process of preparing for interstellar missions could have transformative effects on human self-understanding. The necessity of creating closed-loop life support systems, capable of sustaining human life for decades or centuries without external resources, would require a deep understanding of the complex web of biological and geochemical processes that maintain Earth's habitability. This understanding, in turn, might foster a more integrated view of humanity's relationship with the broader biosphere, recognizing our fundamental dependence on and responsibility toward the complex living systems that sustain us. The development of artificial intelligence sophisticated enough to operate autonomously on decade- or century-long missions would likewise force a re-evaluation of our understanding of intelligence and consciousness. If we create machines capable of adapting to novel situations, making complex decisions, and perhaps even experiencing subjective states analogous to human consciousness, where would we draw the line between tool and fellow sentient being? What ethical responsibilities would we have towards such entities? These questions, already emerging in the field of AI ethics, would become increasingly urgent as we develop the autonomous systems needed for interstellar exploration. The potential for interstellar travel to transform human society extends beyond the philosophical to the practical organization of our civilization. The energy requirements for interstellar missions, particularly human-carrying ones, are enormous, potentially requiring power generation on scales far beyond our current capabilities. Developing such energy sources, whether through advanced fusion, antimatter production, or other technologies, could simultaneously address energy needs on Earth, potentially enabling abundance where scarcity now exists. Similarly, the closed ecological systems needed for long-duration human space missions could inform more sustainable approaches to resource use on Earth. If we can design systems that recycle nearly 100% of their material resources for use in space, we can apply similar principles to terrestrial resource management, reducing waste and environmental impact, while maintaining or improving quality of life. The organizational challenges of interstellar missions might also drive social innovation. Projects spanning centuries would require new forms of intergenerational cooperation and commitment, perhaps leading to the development of institutions designed specifically for extreme long-term planning and management. Such institutional forms could prove valuable for addressing long-term challenges on Earth, from environmental sustainability to the management of potentially dangerous technologies over many generations. Beyond these practical transformations, the symbolic power of reaching for the stars could have profound effects on human motivation and aspiration. Throughout history, grand challenges have inspired human creativity, cooperation, and achievement. The Apollo program, for example, not only achieved its direct goal of landing humans on the moon, but inspired generations of scientists, engineers, and explorers. An interstellar program, as the grandest of grand challenges, could similarly inspire humanity toward achievements beyond our current imagining. This aspirational dimension should not be underestimated. Human societies thrive when oriented toward meaningful goals that transcend individual lifespans. The building of medieval cathedrals, for example, spanned generations, with those laying foundations knowing they would never see the completed structures. Yet this multi-generational project created not just architectural masterpieces, but vibrant communities united by a shared vision. Interstellar exploration offers a similar potential for uniting humanity around goals that transcend individual lifespans, or even individual centuries. It presents a vision of human potential extended across time and space, not confined to a single planet or a few brief centuries of technological civilization. This expansive vision of human possibility might help us transcend the short-term thinking that characterizes much of contemporary politics and economics, fostering a longer view of human flourishing. Of course, the transformative potential of interstellar missions comes with risks as well as opportunities. The enormous resources required might be diverted from pressing needs on Earth, exacerbating inequality if the benefits of space development flow primarily to already advantaged groups. The divergence of human populations across different stellar systems could lead to conflict as well as diversity, particularly if resource scarcity or ideological differences create tensions between Earth and extraterrestrial settlements. Moreover, the technologies developed for interstellar travel could have dual-use potential. Advanced propulsion systems capable of accelerating a spacecraft to a significant fraction of light speed could, if misdirected, become weapons of unprecedented, destructive power. Artificial intelligence sophisticated enough to operate autonomously for decades might pose existential risks if its goals misaligned with human welfare. These risks would need to be carefully managed through appropriate governance structures and ethical frameworks. Yet the risks of reaching for the stars must be balanced against the risks of remaining confined to a single planet. Earth has experienced multiple mass extinction events throughout its history, from asteroid impacts to massive volcanic eruptions. While none of these has yet threatened human existence, they remind us of our planetary vulnerability. Technological civilization faces additional risks, from nuclear weapons to engineered pandemics to the potential disruptions of artificial intelligence. Expanding beyond our solar system would represent a form of insurance against such existential threats, ensuring that human consciousness and culture would continue even if Earth itself became uninhabitable. Beyond this practical risk management, interstellar settlement would offer opportunities for human diversity and experimentation that would be difficult or impossible to achieve within a single planetary system. Different stellar settlements might develop diverse approaches to governance, economics, technology, and culture, creating a kind of laboratory for human social organization. Successful innovations could be shared across the interstellar network, albeit with significant communication delays, while failures would remain localized rather than threatening humanity as a whole. This potential for parallel experimentation extends to approaches to human enhancement and artificial intelligence as well. Different stellar settlements might adopt different policies toward genetic modification, neural interfaces, life extension, or the development of artificial general intelligence. Over time, these diverse approaches would provide insights into the outcomes of different technological choices, informing decision-making across human civilization. The communication challenges of interstellar distances would also transform how information flows across human society. With years or decades of delay between transmission and reception, the rapid back and forth of contemporary digital communication would be impossible between stars. This might foster more careful, considered forms of communication, with messages designed to convey maximum meaning within minimum bandwidth constraints. It might also encourage greater autonomy and self-reliance among stellar settlements, as they would need to solve problems and make decisions without real-time input from Earth. These communication constraints would transform cultural exchange as well. Artistic works, scientific discoveries, and philosophical insights would still flow between stellar systems, but at a pace far slower than we are accustomed to in our globally networked civilization. This might lead to more distinct local cultures, each developing along its own trajectory, while only periodically influenced by ideas from elsewhere in human space. The resulting cultural diversity might exceed anything seen in human history, with each stellar settlement potentially developing art forms, linguistic innovations, and philosophical perspectives uniquely adapted to its environment and history. The biological implications of interstellar settlement are equally profound. Humans evolved under specific conditions on Earth, from its gravity and atmospheric composition to its day length and radiation environment. As we establish presence around other stars, we would encounter environments that differ, sometimes dramatically, from these evolutionary conditions. Over generations, human populations in these different environments would likely undergo both genetic drift, the random changes in gene frequency that occur in any population over time, and selection pressure, in which traits better suited to the local environment become more common. In the near term, these pressures might be partially offset by technology. Habitats could be designed to mimic Earth conditions, with artificial gravity, Earth-like day-night cycles, and radiation shielding. Genetic disorders or adaptations that reduce survival or reproduction could be addressed through medical intervention. However, over longer timeframes, particularly if resources for maintaining entirely Earth-like conditions became constrained, human populations might begin to adapt to their local conditions. This adaptation could occur through natural selection, but more likely would involve deliberate genetic modification or enhancement. As our understanding of the human genome advances, along with our ability to make precisely targeted changes, future generations might choose to modify themselves or their offspring to better thrive in their specific environments. Higher gravity worlds might select for denser bones and stronger muscles. Environments with different radiation profiles might favor enhanced DNA repair mechanisms. Worlds with different atmospheric compositions might lead to modifications in lung structure or oxygen carrying capacity in blood. Over sufficient time, these adaptations could potentially lead to speciation, the evolution of populations so different that they could no longer interbreed with unmodified humans. This possibility raises profound questions about human identity and unity across stellar systems. Would we consider highly adapted populations around other stars to still be human? How would we navigate relationships between populations that might be as different from each other as modern humans are from Neanderthals or even more distant evolutionary cousins? These questions of human unity across biological difference connect to broader philosophical questions about the nature of personhood and moral consideration. As human populations diverge, both culturally and potentially biologically, we would need to develop frameworks for maintaining mutual recognition and respect, despite these differences. This challenge would be further complicated if we develop artificial general intelligence or modify ourselves to the point where the boundary between human and machine becomes blurred. The timeframes of interstellar settlement also force us to confront questions of intergenerational justice and responsibility. Decisions made by current generations, such as which propulsion technologies to develop or which star systems to target for exploration, would constrain the options available to future generations. This creates a form of power asymmetry across time, where earlier generations have disproportionate influence over the conditions in which later ones live. Navigating this asymmetry ethically would require developing frameworks for considering the interests and preferences of people not yet born. It would involve creating institutions capable of maintaining commitments across multiple generations, ensuring that projects begun by one cohort can be completed by their distant descendants. It would necessitate balancing the legitimate authority of the present to make decisions against the right of the future, to inherit a range of meaningful options rather than a narrowly constrained path. These challenges of interstellar ethics are not merely academic, but would have practical implications for how we design missions, allocate resources, and structure decision-making. They would influence everything from the composition of generation ship crews to the governance structures of newly established settlements around other stars. They would shape our approach to potentially habitable worlds, particularly if they already harbor indigenous life, and our relationships with any artificial intelligences or modified humans that emerge as part of our interstellar expansion. Yet alongside these challenges, interstellar travel offers opportunities for ethical growth and maturation as a species. The very act of committing to multi-generational projects requires a kind of moral imagination that transcends immediate self-interest. Planning for the well-being of humans who will live centuries from now, perhaps in environments we can barely imagine, stretches our capacity for empathy and care across time in ways that few other activities demand. Similarly, establishing human presence in multiple stellar systems would require us to think carefully about what aspects of Earth human culture, values, and institutions we wish to preserve, and what we might choose to leave behind or modify. This process of reflective filtering, deciding which elements of our heritage to carry forward and which to transform, offers an opportunity for deliberately shaping our collective future rather than simply allowing it to unfold through the accretion of short-term decisions. The prospect of discovering life beyond our solar system, even if only microbial, would also transform our ethical landscape. Finding a second genesis of life would confirm that life is not unique to Earth, suggesting it might be common throughout the galaxy. This would heighten our sense of responsibility as stewards of Earth's biosphere, which would be revealed as one instance of a phenomenon that, while perhaps common, is still precious and worthy of protection. Should we encounter complex or intelligent life, the transformation of our ethical perspective would be even more profound. Such a discovery would force us to expand our circle of moral consideration beyond humanity and Earth life to encompass truly alien forms of consciousness. It would require us to develop frameworks for communication and cooperation across potentially vast biological and cognitive differences. It would challenge us to find common ground despite the absence of shared evolutionary history or cultural context. Even in the absence of discovering extraterrestrial life, the very act of expanding beyond our solar system would likely transform our relationship with Earth and its biosphere. Seeing Earth from the perspective of other stellar systems, perhaps as nothing more than a faint point of light, indistinguishable from countless other stars, would underscore both its objective insignificance in the cosmic scale and its profound importance as the origin of all known life and consciousness. This paradoxical perspective, recognizing both our cosmic insignificance and our unique value, might foster a more balanced relationship with our home planet and the broader universe. It could help us transcend both hubris, the belief that human concerns are centrally important to the cosmos, and despair, the sense that nothing matters in the face of cosmic vastness. Instead, it might nurture a perspective that embraces our small but real significance as bearers of consciousness in an apparently unconscious universe, with the responsibility that entails. The journey to the stars, then, is not merely a physical expedition, but a moral and spiritual one as well. It calls us to grow not just in technological capability, but in ethical scope and depth. It challenges us to extend our care and concern across vast distances of space and time, to balance our legitimate self-interest with responsibility toward future generations, other life forms, and the cosmos itself. It invites us to become worthy of the stars, even as we reach toward them. As we stand at the threshold of this great journey, let us recognize that the stars have always been more than distant suns to humanity. They have been beacons of navigation, objects of wonder, subjects of scientific inquiry, and symbols of aspiration. They have guided sailors across trackless oceans, inspired poets and philosophers, driven the development of physics and astronomy, and fueled dreams of exploration beyond the confines of our home world. Our reaching toward these stars represents a continuation of this long relationship, an extension of human curiosity and wonder into the physical realm through the vehicles of our technology. Yet it is also something new, a literal rather than merely metaphorical journey beyond the solar cradle that has nurtured all life as we know it. This transition, from a species bound to its birth planet to one with a presence among the stars, would mark a new chapter in the story of consciousness on Earth, perhaps as significant as the emergence of multicellular life or the development of intelligence itself. The changes that this journey would bring, both to those who venture outward and to those who remain, are difficult to fully envision from our current vantage point. Yet we can be confident that they would be profound, touching every aspect of human existence, from our biology and technology to our cultures, societies, and self-understanding. The path to the stars is not merely a trajectory through physical space, but a journey of becoming, a transformation of humanity into something both continuous with our past and radically new. As we contemplate this journey and the changes it might bring, let us approach it with both courage and humility, with boldness of vision tempered by care for the well-being of all who would be affected by our choices. Let us recognize that the stars, for all their distance and difference from our evolutionary home, have been part of the human story since our emergence as a species. They have shone down upon every human generation, a constant presence in our night sky even as civilizations rose and fell, languages evolved and disappeared, and technologies transformed human life again and again. Now, as we develop the capabilities that might allow us to reach these ancient lights, let us carry with us the best of what humanity has learned and created throughout our long journey on Earth. Let us bring not just our technology, but our art, our philosophy, our capacity for wonder and reverence, our ability to find meaning in the cosmos, despite its indifference to our existence. For in this bringing, this carrying forward of human consciousness and culture beyond the bounds of our birth world, we might find a kind of cosmic significance that transcends our physical insignificance among the stars. As we approach the conclusion of our journey through the scientific and technological landscape of interstellar travel, it is fitting that we turn our attention to perhaps the most profound question of all: why? Why venture to the stars at all? What deeper meanings might we find in this grandest of human endeavors? What philosophical insights emerge when we contemplate humanity's potential expansion beyond our solar cradle? In this chapter, we will explore the philosophical dimensions of interstellar travel, examining the motivations, meanings, and metaphysical implications of reaching for the stars. Throughout human history, exploration has been driven by a complex interplay of practical and spiritual motivations. The Polynesian voyagers who navigated the vast Pacific Ocean were seeking new islands for settlement, but their journeys were also embedded in cultural and religious frameworks that gave meaning to their explorations. European expeditions of the 15th and 16th centuries sought trade routes and material wealth, but were simultaneously quests for knowledge, and often framed in religious terms as extending the reach of their faith. The Apollo missions to the moon served geopolitical and scientific purposes, but also represented a kind of spiritual quest to touch another world. Interstellar travel similarly encompasses both practical and transcendent dimensions. At the practical level, expanding beyond our solar system could serve as a form of species-level insurance against catastrophic events on Earth. Even with the most careful stewardship, our home planet faces threats ranging from asteroid impacts to supervolcano eruptions to artificial hazards of our own creation. A human presence around multiple stars would ensure that no single disaster, however severe, could end the human story. This insurance motivation connects to deeper questions about the value of humanity's continued existence. Why should we care whether conscious, intelligent life persists in the universe? What value does human civilization have that makes its continuation worth the enormous effort and resources that interstellar travel would require? These questions have no simple answers but point toward fundamental issues of meaning and purpose that underlie the interstellar project. One philosophical tradition that addresses these questions is cosmic humanism, which sees human consciousness as significant, not just for its own sake, but as the universe's means of becoming aware of itself. In this view, humans are not separate from the cosmos, but are a way that the cosmos experiences and understands its own existence. Our curiosity, our scientific inquiry, our aesthetic appreciation of the night sky represent the universe exploring itself through the vehicle of human consciousness. From this perspective, expanding human presence to other stars would represent an extension of the cosmos's self-awareness across multiple stellar systems. It would be a kind of awakening of the universe, bringing consciousness and understanding to regions that have existed for billions of years without being perceived or comprehended by any sentient being. This view suggests an almost spiritual dimension to interstellar travel, a fulfillment of cosmic potential through the expansion of awareness. A related philosophical framework is found in the writings of Olaf Stapledon, whose novels Star Maker and Last and First Men explore vast futures in which human and posthuman consciousness spreads throughout the galaxy. Stapledon envisioned a kind of cosmic community of minds in which intelligence from many worlds would gradually come together in ever greater unity and understanding, culminating in a direct apprehension of the fundamental nature of reality, which he symbolized as the Star Maker. This vision suggests that the expansion of consciousness beyond Earth might have significance not just for humanity but for the cosmos itself, as part of a grand process of awakening. Such cosmic perspectives connect to more traditional, religious, and spiritual frameworks as well. Many religious traditions include some concept of humans as stewards or caretakers of creation, with responsibilities to understand, appreciate, and potentially extend the reach of consciousness. The Jewish concept of tikkun olam, the repair or perfection of the world, and the Christian notion of humans as co-creators with the divine, participating in the ongoing work of creation, can be interpreted as supporting the expansion of human presence and understanding beyond our planet of origin. Eastern philosophical traditions offer their own perspectives on the meaning of cosmic exploration. Buddhist teachings on interdependence and the illusory nature of separate selfhood suggest that our apparent separation from the cosmos is itself a form of ignorance or misunderstanding. From this viewpoint, the exploration of space might be seen as a kind of return to our true nature, recognizing our fundamental unity with all that exists. The Taoist emphasis on living in harmony with the natural flow of the universe might similarly be interpreted as encouraging an expansion that follows the natural direction of consciousness toward greater awareness and understanding. These various philosophical and spiritual frameworks share a common thread. They suggest that interstellar travel might have significance beyond its practical benefits, representing a kind of fulfillment of human potential or cosmic purpose. They frame the journey to the stars not merely as a physical expedition, but as a meaningful engagement with the deepest questions of existence, consciousness, and value. However, other philosophical perspectives raise important questions and challenges to the interstellar project. Deep ecology and some environmental philosophies, for instance, might question whether humanity has a right to extend its presence to other stellar systems, particularly if doing so would impact existing ecosystems. If we discover life around other stars, what ethical obligations would we have toward it? Would we be justified in altering environments to suit human needs if doing so harmed indigenous organisms, even microbial ones? These questions connect to broader issues of environmental ethics that are already pressing on Earth. How do we balance human needs and aspirations against the preservation of natural systems? What moral status should we accord to non-human life forms, particularly those very different from the familiar animals and plants of Earth? The extension of human presence to other stars would raise these questions in new and perhaps more acute forms, challenging us to develop ethical frameworks that can guide our interactions with entirely novel environments and, potentially, life forms. Post-colonial critiques of exploration also raise important considerations. The history of human exploration on Earth has often been intertwined with domination, exploitation, and the imposition of one culture's values upon others. While interstellar travel would not involve the displacement of human populations, the language and conceptual frameworks we use to discuss it often draw upon this problematic history, with terms like colonization and settlement carrying complex historical baggage. A more thoughtful approach to interstellar expansion would involve critical reflection on these frameworks and the development of new language and concepts that emphasize responsible stewardship, mutual flourishing, and the intrinsic value of the environments we might encounter. It would recognize the potential for harm as well as benefit in human expansion and would prioritize approaches that minimize negative impacts while maximizing positive outcomes for all forms of life involved. Existentialist perspectives offer yet another angle on the interstellar question. In a universe apparently indifferent to human concerns, with no externally imposed meaning or purpose, interstellar travel represents a powerful assertion of human freedom and self-definition. By choosing to venture beyond our solar system, we would be creating meaning through our actions, defining our collective identity as a species that reaches outward rather than turning inward. This self-created meaning may be all the more valuable precisely because it is chosen rather than imposed by external authority or cosmic plan. The French existentialist Albert Camus wrote of Sisyphus, condemned by the gods to roll a boulder up a hill, only to have it roll back down, repeating this task for eternity. Camus suggested that despite the apparent futility of his situation, Sisyphus could find meaning in his struggle, a kind of defiance in the face of cosmic indifference. Similarly, interstellar travel, with all its challenges and uncertainties, might represent a form of meaningful defiance, a refusal to accept the limitations of our planetary origin, and a bold assertion of human possibility in an indifferent cosmos. The German philosopher Martin Heidegger's concept of thrownness, the idea that humans find themselves already existing in a world they did not choose, with constraints and possibilities not of their making, also resonates with the interstellar question. We find ourselves on Earth, within a solar system, subject to physical laws that limit our movement and lifespan. Yet Heidegger also emphasized human freedom within these constraints, our ability to make authentic choices that reflect our deepest values and aspirations. Choosing to reach for the stars might represent such an authentic choice, an expression of human freedom within the constraints of our cosmic situation. Moving beyond Western philosophical traditions, indigenous perspectives from around the world offer valuable insights on humanity's relationship with the cosmos. Many indigenous cultures emphasize deep connections to place, to the specific lands and ecosystems that have sustained their communities for generations. They often view humans not as separate from nature, but as integral parts of larger ecological and spiritual systems, with responsibilities to maintain balance and harmony within these systems. These perspectives raise important questions about interstellar expansion. What would it mean to develop similarly deep connections to places beyond Earth? How might we extend concepts of ecological relationship and responsibility to entirely different environments around other stars? Can the wisdom developed through millennia of human relationship with Earth be translated to guide our interactions with other worlds? Or would entirely new frameworks be needed? The answers to these questions are not simple or straightforward, but the questions themselves highlight the richness and complexity of the philosophical dimensions of interstellar travel. They remind us that the journey to the stars is not merely a technical challenge, but a profound human endeavor that touches on our deepest values, beliefs, and understandings of ourselves and our place in the cosmos. Beyond these various philosophical frameworks, interstellar travel also raises fascinating metaphysical questions about the nature of time, distance, and human identity. The vast timescales involved in journeys to even the nearest stars, measured in decades or centuries with foreseeable technology, challenge our conventional understanding of human projects and purposes. Most human endeavors are planned with timeframes of years, or at most decades, reflecting the limits of individual human lifespans. Interstellar missions would transcend these limits, requiring planning and commitment that span generations. This temporal extension raises questions about personal and collective identity over time. In what sense would a mission that takes centuries to complete, with its original planners long dead before its conclusion, be the same project at its end as at its beginning? How would the meaning and purpose of such a mission be maintained across multiple generations, particularly if those born during the journey never experienced either the departure world or the destination? These questions connect to deeper philosophical issues about the nature of personal and collective identity through time, issues explored by thinkers from John Locke to Derek Parfit. Similarly, the vast distances involved in interstellar travel challenge our understanding of human community and connection. Current human societies are bound together by networks of communication, trade, and cultural exchange that operate on timescales of days or at most weeks. Interstellar distances would stretch these connections to breaking point, with communication delays of years or decades between stellar systems. This would necessarily lead to greater autonomy and differentiation between human communities separated by such distances. The philosopher Thomas Nagel has written about the difficulty of imagining experiences very different from our own, using the example of bat echolocation to illustrate how the subjective experience of other beings may be fundamentally inaccessible to us. Interstellar separation might eventually create a similar inaccessibility between human communities around different stars, with distinct environments, histories, and potentially even biological adaptations or technological enhancements. Stellar communities might eventually develop subjective experiences so different that true mutual understanding becomes difficult or impossible. This possibility connects to philosophical work on incommensurability, the idea that some conceptual frameworks or ways of experiencing the world may be so different that they cannot be directly compared or translated between. The philosopher of science Thomas Kuhn proposed that different scientific paradigms might be incommensurable in this way, making it difficult for scientists working within different frameworks to fully understand each other's perspectives. Interstellar separation might eventually create a similar incommensurability between human cultures around different stars, each adapted to its unique environment and history. Yet alongside these challenges to human unity and mutual understanding, interstellar expansion also offers possibilities for new forms of connection and meaning. The sociologist Emil Durkheim observed that human societies are bound together not just by practical necessity, but by shared beliefs, rituals, and symbols that create a sense of collective identity and purpose. The very fact of being part of humanity's expansion beyond our solar system might serve as such a binding principle, creating a sense of shared cosmic identity despite the vast distances and differences between stellar communities. This points toward a kind of cosmic consciousness that transcends the limitations of individual human perspective. The Russian cosmist philosopher Nikolai Fedorov proposed a vision of humanity working together to conquer death and resurrect all past generations, ultimately transforming the cosmos into a realm hospitable to immortal human life. While his specific vision may seem fantastical, it represents an important philosophical tradition that sees human technological advancement, including space exploration, as part of a broader project of cosmic transformation with spiritual as well as practical significance. Contemporary philosophers like Nick Bostrom have updated these cosmist themes, examining the long-term possibilities for humanity's expansion throughout the galaxy and beyond. Bostrom's concept of astronomical waste suggests that failing to expand beyond Earth would represent an enormous lost opportunity, leaving the vast resources of other stellar systems unutilized for the flourishing of consciousness and value. This perspective frames interstellar expansion not just as a possible path for humanity, but as a moral imperative, a responsibility to realize the cosmic potential for consciousness and value. However, this expansionist vision has been challenged by other philosophical perspectives. The cosmic humility advocated by environmental philosophers like Holmes Rolston III suggests that human values and interests should not automatically take precedence over those of other entities or systems. From this perspective, expanding human presence throughout the galaxy might represent a kind of cosmic hubris, imposing our particular form of consciousness and value on environments that might develop their own forms of complexity and worth if left to their own evolutionary pathways. These contrasting perspectives highlight a fundamental philosophical tension in the interstellar project between human exceptionalism, which sees human consciousness as uniquely valuable and worthy of cosmic expansion, and cosmic humility, which recognizes the limitations of human perspective and the potential value of non-human forms of existence. Navigating this tension thoughtfully would be essential for an ethically sound approach to interstellar expansion. The tension connects to even deeper philosophical questions about the nature of value itself. Is value something that exists objectively in the universe, independent of conscious observers, or is it created or recognized by consciousness? If the latter, does this give special significance to the expansion of consciousness into previously unconscious regions of the cosmos, bringing value where none existed before? These questions have been explored by philosophers from Plato to G.E. Moore to contemporary value theorists, without achieving consensus. What seems clear, however, is that interstellar travel would represent a profound engagement with these fundamental questions of value, meaning, and purpose. It would require us to articulate and refine our understanding of why consciousness matters, why exploration and discovery are valuable, and what responsibilities come with the power to extend our presence beyond our planet of origin. This philosophical dimension of interstellar travel connects to the human search for meaning in a vast and largely indifferent cosmos. The physicist Steven Weinberg famously wrote that the more the universe seems comprehensible, the more it also seems pointless. Yet he also acknowledged that humans create meaning through their values, aspirations, and actions, even in a universe without inherent purpose. Interstellar travel represents a powerful assertion of such human-created meaning. By venturing beyond our solar system, we would be declaring that exploration, discovery, and the expansion of consciousness have value despite their cosmic insignificance. We would be affirming that the human story matters not because of its physical scale or cosmic importance, but because of its meaning to us, the conscious beings who experience and create it. This connects to the philosophical concept of cosmic pessimism, explored by thinkers like Eugene Thacker and Thomas Ligotti, which confronts the apparent meaninglessness and indifference of the universe to human concerns. Interstellar travel can be seen as a response to this pessimism, not denying the vastness and impersonality of the cosmos, but affirming that human meaning and value can exist within it nonetheless. It suggests that the apparent cosmic void is not a reason for despair, but an opportunity for expansion, discovery, and the creation of new forms of meaning. The philosopher and novelist Iris Murdoch wrote that love is the extremely difficult realization that something other than oneself is real. Interstellar exploration embodies this difficult realization on a cosmic scale, acknowledging the reality and potential significance of worlds, environments, and possibly beings very different from ourselves and from our familiar earthly context. It represents an extension of human care and concern beyond the boundaries of our planet, an expansion of our moral imagination to encompass the truly other. This expansive moral imagination connects to philosophical work on the overview effect, the cognitive shift reported by astronauts who have seen Earth from space. This shift involves recognizing both the fragility and unity of our home planet and the artificial nature of the boundaries we draw between nations, cultures, and even species. Interstellar travel might induce an even more profound shift, helping us recognize our common identity, not just as Earthlings, but as conscious beings in a largely unconscious cosmos, bearers of awareness in the vast cosmic darkness. The philosopher Charles Taylor has written about strong evaluation, the human capacity to make judgments not just about what we want or prefer, but about what is truly worthy or valuable. Interstellar travel would engage this capacity at the deepest level, requiring us to articulate and act upon our strongest evaluations about what aspects of human civilization are worth preserving and extending beyond our solar system. It would force us to distinguish between the merely habitual or convenient aspects of our cultures and those that represent our deepest values and insights. This process of strong evaluation connects to philosophical work on cultural evolution and transmission. The philosopher of science Daniel Dennett has proposed that cultural ideas, or memes, evolve through a process analogous to biological evolution, with some ideas being more successful at replication than others. Interstellar expansion would create new selective pressures on human cultural ideas, potentially favoring those that support successful adaptation to novel environments and social situations. This might lead to a kind of cultural flourishing, with new forms of art, science, philosophy, and social organization emerging in response to the unique challenges and opportunities of interstellar existence. The possibility of encountering non-human intelligence, whether through discovering extraterrestrial life or through creating artificial general intelligence, adds another dimension to the philosophical significance of interstellar travel. Such encounters would force us to expand our understanding of intelligence, consciousness, and moral consideration beyond the human paradigm. They would require us to develop frameworks for communication, cooperation, and ethical relationship with beings, potentially very different from ourselves in their cognitive structures, values, and ways of experiencing the world. The philosopher Immanuel Kant proposed a kingdom of ends, a moral community in which all rational beings are treated as ends in themselves, rather than merely as means to others' goals. Interstellar expansion might eventually create a literal kingdom of ends, spanning multiple stellar systems, encompassing various forms of consciousness, both human and non-human, united by mutual recognition and respect, despite potentially vast differences in their natures and origins. This vision connects to contemporary philosophical work on the long now, a perspective that considers human civilization on timescales of thousands or even millions of years rather than the decades or centuries that typically frame our thinking. The long now foundation, established by philosopher and computer scientist Daniel Hillis, among others, promotes such long-term thinking through projects like a clock designed to run accurately for 10,000 years, marking time on a scale that transcends individual human lives and conventional historical periods. Interstellar travel, with its multi-generational timeframes and potential for establishing human presence that could last for eons, represents the long now perspective in its most expansive form. It asks us to consider not just the immediate future of humanity, but our potential trajectory over thousands or millions of years of cosmic evolution and expansion. It invites us to become ancestors whose decisions and actions will shape the lives of countless future generations across potentially thousands of worlds. This ancestral responsibility connects to philosophical work on intergenerational justice, which examines our ethical obligations to future generations. The philosopher John Rawls proposed a veil of ignorance thought experiment, asking us to design principles of justice without knowing which position in society we would occupy. Extended to the intergenerational context, this might ask us to make decisions about interstellar expansion without knowing whether we would be the initiators of such missions or the descendants who must live with their consequences generations later. Such thought experiments highlight the asymmetric power relationship between present and future generations. Those currently alive can make decisions that profoundly constrain the options available to future generations, yet those future people have no voice in these decisions. This creates a special responsibility for the present to consider the interests and potential values of those who will come after us, a responsibility particularly acute in the context of multi-generational projects like interstellar travel. These philosophical dimensions of interstellar travel suggest that the journey to the stars is not merely a technical challenge or even a scientific endeavor, but a profound human project that engages our deepest values, aspirations, and understandings of ourselves and our place in the cosmos. It requires us to confront fundamental questions about meaning, purpose, identity, and responsibility, questions that have occupied philosophers throughout human history, but that take on new forms and urgency in the context of potential cosmic expansion. As we contemplate voyages to the stars, let us recognize that these philosophical questions are not mere abstractions but practical considerations that would shape the nature and success of any interstellar mission. The motivations we bring to such endeavors, the values we seek to express and preserve through them, the meanings we find in the vast cosmic journey, would all influence how we design and execute these missions, and how they ultimately transform human civilization. The stars have beckoned to humanity throughout our existence, inspiring wonder, curiosity, and aspiration across countless generations and cultures. From the ancient astronomers who mapped their movements to the modern scientists who study their composition and life cycles, from the poets who have used them as metaphors for human yearning to the engineers now designing spacecraft that might one day reach them, the stars represent a kind of universal human heritage, a shared object of fascination that transcends cultural and historical boundaries. As we develop the technological capabilities that might allow us to bridge the vast distances between ourselves and these ancient lights, let us carry with us not just our scientific knowledge and engineering skill, but also the philosophical wisdom developed through millennia of human reflection on meaning, value, and purpose. Let us approach the stars not merely as physical destinations, but as invitations to expand our moral imagination, deepen our understanding of ourselves, and create new forms of meaning in a cosmos that offers no meaning but what we bring to it. The journey to the stars is, at its deepest level, a journey of becoming, a process through which humanity might evolve not just technologically but philosophically, developing more expansive perspectives, more inclusive forms of care and concern, and more enduring sources of meaning and purpose. It invites us to grow into a species worthy of the cosmic voyage, one that brings not just intelligence, but wisdom to the silent worlds around other suns. As we conclude our philosophical exploration of interstellar travel, let us recognize that the cosmos itself exists in a kind of dialogue with human consciousness. The stars shine regardless of whether we observe them, but they take on meaning, significance, and value through our perception and understanding. When we look at the night sky, we transform points of light into objects of wonder, curiosity, and aspiration. When we contemplate journeys to these distant suns, we transform physical destinations into symbols of human potential and cosmic destiny. This dialogue between consciousness and cosmos represents perhaps the deepest significance of interstellar travel. It is a conversation that has continued throughout human existence, from the first hominids who gazed at the night sky in wordless wonder to the contemporary scientists and philosophers who contemplate the nature and future of our cosmic journey. The stars have always been there, patient and eternal by human standards, waiting for us to develop the capabilities and the wisdom to reach toward them. not just with our technologies, but with our understanding, our imagination, and our care, whatever specific form our interstellar endeavors might take in the coming centuries. Whether small robotic probes racing between the stars or vast generation ships carrying thousands of humans to new homes around other suns, they will be expressions not just of our technical prowess, but of our philosophical maturity. They will reflect our understanding of what matters in the cosmos, what aspects of humanity are worthy of preservation and extension, and what responsibilities come with the power to expand beyond our planet of origin. As we stand at the threshold of this grand cosmic journey, let us approach it with both boldness and humility, with confidence in human capability and awareness of human limitation, with excitement about the possibilities that await us and care for the worlds we might encounter. Let us recognize that the journey to the stars is not merely about reaching distant physical destinations, but about becoming the kind of species that can undertake such journeys with wisdom, responsibility, and a sense of cosmic purpose. The stars are waiting, as they have waited throughout human history. The question is not whether they will remain, but whether we will rise to the challenge they represent, developing not just the technological capabilities, but the philosophical maturity to extend human presence and awareness beyond our solar cradle into the wider cosmic community. This is the invitation the stars offer us, the promise they hold, and the challenge they present, to become worthy of the journey, not just technologically, but philosophically, to grow into a species that brings not just intelligence but wisdom to the silent worlds around other suns. As our journey through the challenges, possibilities, and implications of interstellar travel draws to a close, we find ourselves standing at the threshold of what may be humanity's greatest adventure. We have explored the vast distances that separate us from even our nearest stellar neighbors, the propulsion technologies that might one day bridge these cosmic gulfs, the comparative merits of robotic and human missions, and the philosophical dimensions of reaching for the stars. Now, as we conclude, let us reflect on what this grand endeavor might mean for our species and how we might take our first tentative steps toward a future among the stars. The story of life on Earth has been one of gradual expansion, from the first single-celled organisms in ancient oceans to the complex biosphere that now encompasses every corner of our planet. Human beings, as part of this larger story, have extended their presence from our African origins to every continent, developing technologies and social structures that allow us to thrive in environments from tropical forests to Arctic tundra. Our ventures into space represent the continuation of this expansive journey, reaching beyond the atmosphere that has bounded life on Earth for billions of years. Yet the leap from our current presence in near-Earth orbit and occasional forays to the Moon to true interstellar travel represents a discontinuity, a threshold crossing unlike any in our previous experience. The distances involved are so vast, the time frame so extended, and the technological challenges so formidable that interstellar missions will require fundamentally new approaches to spaceflight, mission planning, and perhaps even to how we conceive of ourselves as a species. This threshold nature of interstellar travel suggests that we should approach it not as a single giant leap, but as a series of incremental steps, each building upon the last, each extending our reach and capabilities a bit further into the cosmic ocean. The path to the stars begins not with a sudden departure from our solar system, but with the patient development of the technologies, knowledge, and philosophical maturity that will eventually enable such journeys. What might these steps look like? Perhaps the first would be the establishment of a permanent human presence on the Moon and Mars, creating settlements that could serve as proving grounds for the closed-loop life support systems, sustainable governance structures, and long-term planning capabilities that would be essential for any interstellar mission. These nearer destinations, while challenging in their own right, offer opportunities to develop and test technologies in environments beyond Earth, while still remaining within reach of resources and assistance from our home planet. Simultaneously, robotic missions to the outer solar system and beyond would continue to expand our knowledge of the space environment and help develop the autonomous systems that would be crucial for interstellar probes. Missions to the Kuiper Belt, the heliopause, and the inner Oort cloud would push the boundaries of our exploratory capabilities while providing valuable scientific data about these little understood regions of our solar system. These robotic pathfinders might eventually be followed by the first tentative ventures into truly interstellar space, perhaps in the form of small, fast-moving probes like those envisioned by the Breakthrough Starshot initiative. These initial ambassadors, racing through neighboring stellar systems at significant fractions of the speed of light, would provide our first close-up glimpses of other stars and their planets, transforming these distant lights in our night sky into real places with their own unique characteristics and potential. The data returned by these first interstellar missions, though limited by the constraints of communication across light years, would inform more ambitious subsequent efforts. If Proxima Centauri b, for example, shows signs of potential habitability or even life, it might become the focus of more sophisticated follow-up missions designed to orbit rather than merely fly by, allowing for extended study of this tantalizing nearby world. Gradually, over decades or perhaps centuries, our presence in nearby interstellar space would expand, first through increasingly capable robotic missions, and eventually, if the technological challenges can be overcome, through human expeditions. These human missions, whether in the form of generation ships, suspended animation voyages, or some approach not yet conceived, would represent the fulfillment of an ancient dream, the physical presence of human beings around another star for the first time in our species' history. Yet, even as we contemplate this grandest of journeys, we should recognize that the impact of interstellar travel will be felt long before the first human sets foot on a world orbiting another sun. The very act of preparing for such missions, of developing the necessary technologies and organizational structures, will transform life on Earth in ways both obvious and subtle. Consider the technologies required for interstellar travel: highly efficient recycling systems to maintain closed-loop life support, advanced artificial intelligence for autonomous decision-making, fusion or antimatter power sources to provide the enormous energies needed for propulsion, and materials capable of withstanding the harsh conditions of interstellar space for decades or centuries. Each of these, developed initially for space applications, would likely find uses on Earth as well, potentially addressing challenges from resource scarcity to climate change to energy production. Similarly, the organizational innovations needed to plan and execute multi-generational projects might influence how we approach other long-term challenges facing humanity. The ability to maintain focus and commitment across decades or centuries, to balance the needs of the present against those of the far future, would be valuable not just for interstellar missions, but for addressing issues like environmental sustainability, nuclear waste management, and the preservation of knowledge and culture across time. Perhaps most profoundly, the philosophical perspective fostered by serious consideration of interstellar travel might reshape how we understand ourselves and our place in the cosmos. The recognition that human consciousness represents something precious in an apparently unconscious universe, that our capacity for wonder, appreciation, and understanding gives meaning to worlds that would otherwise exist in unseen silence, might encourage a deeper appreciation of consciousness itself, whether human or non-human, as something worthy of preservation and extension. This perspective shift might foster greater care for the Earth and its myriad life forms, not out of instrumental necessity, but from recognition of their intrinsic value as expressions of the complex, beautiful processes that have shaped our world. It might encourage us to see ourselves not as separate from nature, but as nature become aware of itself, with both the freedom that awareness brings and the responsibility to use that freedom wisely. As we take our first steps toward the stars, let us carry with us this expanded perspective, this recognition of both our cosmic insignificance in terms of physical scale and our potential significance as bearers of awareness in an apparently unconscious cosmos. Let us approach interstellar travel not as conquerors staking claim to new territories, but as explorers and students, seeking to understand and appreciate the diverse worlds that orbit other suns, while sharing the gift of consciousness with places that have existed for billions of years without being perceived or understood. The stars have shone down upon Earth since before humans existed to gaze up at them. Their light has illuminated every chapter of our species' story, from our emergence as a distinct lineage to the development of agriculture, writing, and science. From our first tentative use of tools to our modern technological society, they have inspired wonder, guided navigation, driven scientific inquiry, and fueled imagination across countless generations and cultures. Now, as our technological capabilities begin to approach the threshold where journeys to these ancient lights become feasible, we stand at a pivotal moment in the human story. The decisions we make in the coming decades and centuries about whether and how to reach for the stars will shape not just the future of space exploration, but the long-term trajectory of human civilization and perhaps consciousness itself in our corner of the galaxy. This is a responsibility to be approached with both enthusiasm and humility, with boldness of vision tempered by care for the worlds we might encounter and the beings, human and perhaps otherwise, who would be affected by our choices. It requires us to balance the legitimate drive to expand our presence and understanding with recognition of our limitations and the potential value of what exists beyond our current knowledge or control. Yet despite these complexities and responsibilities, the prospect of interstellar travel remains one of the most inspiring and hopeful visions for humanity's future. It suggests that our story need not be confined to a single world, that the light of human consciousness might eventually illuminate places far beyond our solar cradle, and that the wonder and appreciation we feel when gazing at the night sky might someday be directed toward those same stars from planets orbiting them. This vision connects us to something beyond ourselves, to timescales longer than human generations and distances greater than we can truly comprehend. It reminds us that we are part of a cosmic process unfolding over billions of years, a process that has produced, through mechanisms both random and lawful, beings capable of wondering about their origins and contemplating their future among the stars. As we come to the end of our own journey through the landscapes of interstellar travel, from the technical challenges of propulsion to the philosophical implications of cosmic expansion, let us hold on to this sense of wonder and possibility. The stars are distant, but not unreachable. The journey will be long and difficult, but not impossible. The challenges are formidable, but not insurmountable. With patience, creativity, and sustained effort, humanity may yet find its way to the stars, extending our presence and awareness beyond the bounds of our solar system to touch other worlds orbiting other suns. Whether through robotic emissaries carrying our instruments and artificial intelligence, or through human crews venturing forth in generation ships or other vehicles not yet conceived, we may someday bridge the vast gulfs of interstellar space, transforming those distant points of light in our night sky into real places known and experienced by human consciousness. This journey, should we choose to undertake it, will not be completed in a single human lifetime or even several. It represents a multi-generational project that would extend across centuries, each step building upon those before, each generation contributing to a goal whose fulfillment they might not live to see. Yet this very quality, this transcendence of individual human lifespans, gives the interstellar project a kind of meaning and significance beyond more immediate concerns. In a world often dominated by short-term thinking and immediate gratification, the vision of interstellar travel reminds us that humanity is capable of longer perspectives, of care and commitment that extend beyond individual lives to encompass the well-being and flourishing of generations yet unborn. It suggests that we can be more than consumers focused on momentary desires, that we can act as stewards and creators, building something that will outlast us and benefit those who come after. This is perhaps the deepest significance of our reach for the stars, not just the practical benefits of technological development or the scientific knowledge gained through exploration, but the expansion of human moral and temporal imagination to encompass timescales and distances far beyond our everyday experience. In stretching toward the stars, we stretch our conception of who we are and who we might become, expanding the circle of our concern and the horizon of our aspirations. The journey to the stars begins with a thought, a recognition of possibility that transforms those distant lights from mere points in the night sky to potential destinations. It continues with the development of the technologies organizations, and philosophical frameworks needed to bridge the vast gulfs of interstellar space. And it culminates perhaps centuries from now in the presence of human consciousness, whether embodied in biological humans or in our mechanical or digital descendants around other suns. Each step in this journey represents both an achievement in itself and a foundation for what follows. The robotic probes we send to nearby stars, the habitats we establish within our solar system, the propulsion technologies we develop for interplanetary travel, the philosophical perspectives we cultivate through consideration of cosmic timescales and distances all contribute to the larger project of expanding human presence and awareness beyond our planet of origin. As we take these steps, let us remember that the stars are patient. They have shone for billions of years before humans existed to perceive them, and they will continue to shine for billions more. They do not demand our immediate presence, but offer a standing invitation, a perpetual challenge to grow into a species capable of reaching them, not just technologically, but morally and philosophically as well. This patience of the stars gives us both freedom and responsibility, freedom to develop at our own pace, to take the time needed to address challenges on Earth, even as we reach outward, to ensure that our expansion is sustainable and beneficial rather than hasty and harmful. Responsibility to preserve the option of interstellar travel for future generations, to maintain the knowledge, resources, and environmental conditions that would make such journeys possible, and to approach the cosmos with care and humility rather than reckless exploitation. The path to the stars is long, the journey measured in generations rather than years. Yet with each step along this path, we move closer to a future in which human consciousness spans not just one world but many, in which the light of awareness illuminates planets orbiting distant suns, and in which the ancient light of the stars is met with the light of understanding from beings capable of appreciating their beauty and significance. This future awaits us, not as an inevitable destiny, but as a possibility to be realized through sustained effort, scientific advancement, and philosophical maturity. The stars are distant, but not unreachable. We have begun the journey, and though the road ahead is long, each step brings us closer to that moment when humans might look up at a different sun from the surface of a world orbiting another star, the moment when we truly become a multistellar species. Until that day, we continue to dream, to plan, to build the foundations for those who will come after us. We develop the technologies that will one day bridge the gulf between stars. We cultivate the perspectives that will guide our expansion into the cosmos. We tell the stories that keep the vision alive across generations. And we gaze up at the night sky with wonder, knowing that those distant points of light are not just stars but potential destinations, places that might someday feel the touch of human curiosity and consciousness. They may be light years away, but the journey begins with a thought. One day we will send a whisper, then a spark, then ourselves. Until then, we dream. Sleep well toward the stars.